What did Dan said? Oh, I didn't hear what she said. Yeah.
Yeah. Hello. Can you hear me?
Yeah, now I can hear you.
Yeah.
Yeah.
Yeah, we can hear you.
Okay. Maybe we can start first. There are still six professors on the way.
Okay. Yeah.
So
Well, it
sorry.
takes us a few minutes anyway. So yeah. So
Uh,
yeah. So let me get started. It's already 7:53. So good morning or good evening for many participants in the US. So I'm Jian Qing Fang, Frederick Moore Professor of Finance and the Professor of Operations Research and Financial Engineering at Princeton University. So let me first extend a warm welcome to this very conference on statistical machine learning in modern AI, hosted by Tianyuan Mathematical Center in northwestern China, in the lovely city of Xi'an, full of history and traditions. So Xi'an apparently is one of my favorite cities, and I have many fond memories being there. It is very unfortunate this time many of us cannot be there due to COVID-19 pandemic. But apparently, the program is no inferior just because of, COVID-19 pandemic. So indeed, I just realized today that I'm one of the co-organizer of this very conference. I really mean is that I did very, very little work other than suggesting a few speakers. Really, the heavy lifting job rely on Huntu Zhu of UNC Chapel Hill and Dan Dan Jiang of Xi'an University. So I'll let them say a few additional words about the program and the local logistics. So clearly, we are at the age of big data and AI, right, which involves interactively and dynamically collecting data, learning unknown nature and systems, and making optimal decision. So there are enormous amount of empirical successes such as AlphaZero, face recognitions, automatic driving, machine translations, object manipulation, and so on and so forth. But there are many problems remain to be solved. So the title of Susan Murphy's talk on what we use RL, but did it work? I think this is a very interesting, quite a telling title. So in addition to algorithms and the computational costs, right, there are still many foundation problems that remain widely open. So with this background, the center organized a series of high-level academic activities focusing on optimization methods and artificial intelligence. And when I made a suggestion job, right? So the principle usually is whoever made a proposal had to do the work. So this is probably explain why I got involved with this program. But more interestingly, or of course, more tellingly, I have as well as a vast interest in this fascinating area of Markov decision processes, which integrates digital learning and optimization into the heart. So I really like this area, and there's a lot of progress has been made during the past few years. So due to the vast decision spaces and high dimensional nature of reward and value functions, fueled by the demands on algorithmic fairness, robustness, and uncertainty quantification, statistical modeling and machine learning have now become the hearts and CPUs of AI algorithms. Statistical thinking on the data collection, modeling, and analysis, right, so are vital to the next generation of AI. Statistical optimization, which takes statistical task into account when you do optimization, is certainly fundamental to algorithmic design of AI. So without any doubt, statistics is one of the core components to the success of next generation of AIs. So as an important component of data science, statistical encompasses a vast areas, right, from designs of data collection to fundamental limits on data information. So we cannot possibly include all the areas of statistics in this program. Rather, we pick 5 important areas, like statistical machine learning, deep learning, probability inference, statistical optimization, as well as statistical applications to showcase some of statistical efforts in AI. So omission and negligence are inevitable. Statistics and AI itself will occupy at least a 1-year academic program. So there's really, really more to talk than what we really been able to present here. So I personally very much enjoy reading these scientific programs. It contains 30 talks, or maybe a little bit over 30 talks and panel discussions, covering all the topics that we mentioned above. And what I really amazed is by the quality of the papers, also the speakers. So we all know that the conference cannot be successful without earnest support from enthusiastic participants. Some of you travel very far to Xi'an. This probably hasn't arrived yet. And most of us put the busy schedule aside to make this conference a success. I really appreciate all of your efforts and support. And the conference certainly cannot be functioned without a strong local organization. So I would like to take this opportunity to thank, in particular, Dan Jiang and her team, who has devoted so much time to make this symposium possible. And then, of course, the program cannot be in place without dedication of co-organizers like Professor Huntu Zhu and Dan Jiang herself, whose conscientious efforts and enthusiasm on the planning and organization make this conference very exciting and scholastic. So let's give Huntu and Dan a big round of applause. Thank you, Huntu and Dan. So the program put together by our host is truly remarkable and interdisciplinary. I'm really confident that we'll have abundant, open, fruitful, and sometimes even heated, but healthy deep exchanges on the issues concerning all of us. With the diverse subject background, will make this symposium a great success, and the next 3 days are fond and memorable memories for all of us. Thank you very much. And let me see if Huntu have additional remarks want to say, Huntu.
No, I think I'm fine with that. I think I just want to thank the Qianyuan Mathematical Centers for give us this opportunity to organize this important event for statistics. And also I want to thank all the speakers. And without your involvement, we cannot have such a wonderful program. Thank you.
Thank you, Huntu, for the work. Dan, do you have any local logistics you want to announce, or you'll do that later?
Nothing more. And thank you everyone to attend this conference. Thank you for the effort, Professor Fan and Professor Zhu. Okay, thank you.
Thank you, Dan, for the work. You are really the heavy lifting person. So Huntu, now I turn the podium to you. There's no actual podium to be turned, but now is your session.
Okay, thank you everyone. It's good morning or good night, and today this is first section, and it's my great honor to introduce our first speaker, Professor Michael Kosorok, and from our Department of Biostatistics at the UNC Chapel Hill. And I have known Michael for almost 15 years, and Michael Kosorok is the W.R. Callan and John, the Distinguished Professor of the Biostatistics and Professor of Statistics and Operation Research at the UNC Chapel Hill. He received his PhD in Biostatistics from University of Washington in 1991. He's an international known biostatistician and prominent expert in data science, machine learning, precision medicine. He's a fellow of the American Statistical Association in the Institute of the Mathematical Statistics and the American Association for Advancement of the Sciences. He has published around 200 peer-reviewed articles, written a major text on the theoretical foundation of the empirical process and the semi-primary inferences. He's well cited and a co-editor and a book and a research monography on the dynamic treatment regimes and precision medicine. Now is welcome, Michael. It's your turn.
Thank you,
Michael.
Hong Tu. I'm going to share my screen. Can you all see it? Can people see this?
Yes.
Yes. Yeah.
yes.
Good. Yeah. Mhm.
Great, great. So I'll thank you for the invitation. I'm thrilled to be here. It's a very prestigious list of speakers, and I'm very honored. I'm going to be talking about how to look at multiple utilities when we're doing decision support, data-driven decision support in the context of precision health. So first, I'll talk a little bit about incorporating patient preferences in dynamic treatment regime estimation. And then I'm going to talk about how to, a new sort of variation on inverse reinforcement learning, how to learn what physicians are trying to do when they're balancing multiple attributes or outcomes, and how to then learn how to help them do that better. So we'll begin with the first talk about patient preferences. A dynamic treatment regime tailors treatments to individual patient characteristics. This is one of the major ways that we provide decision support for machine learning in precision medicine. And the patient characteristics we would include may involve clinical information as well as patient preferences in terms of outcomes. So if you recall, an optimal dynamic treatment regime maximizes the expectation of a pre-specified clinical outcome if it's applied to all patients in a population of interest. While this definition of optimality is mathematically convenient, it does not directly allow for shared decision-making where patient preferences are integrated into the decision process. So including patient preferences in treatment selection indirectly is mathematically, in a mathematically rigorous way, is important. I want to specify here, we're not asking the patients to give their opinion about what treatment they should receive, because we don't know in advance exactly how that treatment will affect that patient. We are asking their preferences in terms of what outcomes are important to them. How do they balance different competing outcomes, and what is it that they value most in terms of what they care about, in terms of what outcomes are maximized. And this is a way to facilitate patient-centered care, in which patients play a key role in decision-making and evaluation of their own outcomes. It also offers a principled means for matching patient preferences to an optimal dynamic treatment based on potentially complex outcome profiles. Now, one challenge is, how do we elicit patient preferences in doing this? This is not necessarily straightforward. It would be convenient if patients could choose parameters indexing a composite outcome in such a way that they know they'll be happy if that's maximized. That's not possible without specialized training. An alternative approach is to administer a questionnaire or some instrument populated with items that are accessible to a patient in a domain context, yet are informative about preferences in the outcome space. This could be through item response approaches or discrete choice approaches. And I'll be talking a little bit about some work in this direction in Butler, Labor, Davis, and Kosrock, a 2018 biometrics paper that incorporates this approach through the use of item response approaches to help obtain patient preference sensitive optimal dynamic treatment regimes. So we're going to look at how they do this. And we're going to work with IID observations. And the data will consist of these 5 components. W is an element of a p-dimensional instrument that includes p items. It's a questionnaire that helps us assess the relative priority of 2 different outcomes. X are the pre-treatment patient covariates. These are the tailoring variables that we want to use in our dynamic treatment regime algorithm. We have 2 treatments coded -1 and 1. These results can be extended to more complex setting with more treatments, but we're going to focus just on the single treatment case for simplicity of presentation. Then we have 2 outcomes instead of the usual 1, Y and Z. And the dynamic treatment regime we're going to develop is going to be taking a function that takes the domain of the possible answers to the item response instrument and also their tailoring variables, and gives us what treatment we should give that patient. And so to define an optimal dynamic treatment regime in this context, we assume that each individual in the population has a latent preference H that indexes a utility function U that is a combination of the two outcomes Y and Z. This helps us know how to correctly balance these two outcomes. So maximizing U will give us the treatment response that will benefit the patient desires. Now we assume that utility function induces an ordering on Y and Z, so that patients with preference H would prefer outcome Y and Z to Y prime Z prime if U is greater than, if the utilities are ordered. So this gives us ability to order a two-dimensional space. We're going to use Y star to denote potential outcomes. So we're in a causal inference framework with potential outcome approach. U is the potential outcome for the utility function, which is a function of the potential outcomes of the two constituent outcomes. And we're going to define a utility function as follows. It essentially tells us what is the expected value of that utility under the assumption that patients are treated according to the dynamic treatment regime pi. And expectations taken with respect to the joint distribution of XWH A and the potential outcomes. So H is this latent trait that we don't observe, but we hope to get information about that tells us the patient preferences. The optimal DTU, of course, satisfies it having the maximum expectation over all possible policies. Now we're going to assume at first the utility function has the following form. It's basically a linear combination of Y and Z with weighting determined by phi of H, where phi is a cumulative standard normal. H is some patient level variable. It's usually not observed. And the idea is that the relative odds of these phi functions will tell us how much more for a patient who feels H values Y versus Z. Now, linear utility is a common assumption in multi-objective optimization. However, the assumption of a constant gain in utility per unit increase in outcome may not be reasonable in some contexts. In other words, we want to interrogate this linearity assumption a little bit. And so we're going to talk about this briefly. It turns out that for any rational utility, it can be expressed as a linear utility. And so this is an important result. We prove in this paper that any rational utility can be expressed as a linear combination of these two outcomes. And to state this formally, we need to have a little bit of notation. Let R of Z, Wx be the difference in treatment 1 versus 2 in terms of conditional expectation for the outcome Z given W and X. And Ry is similar for Y. And if we were to assign somebody treatment according to the sign of RZ, that would be the Bayes rule and give us an optimal outcome for Z. Likewise, if we do it for using Ry, we'll get the optimal treatment rule. And for the utility U, we would need to take the utility-based version of this, conditioning on that utility. And then the optimal algorithm in that case would be the sign of this. So this is the base idea. And here's a statement of the theorem using these ideas. Assume that for any W and X, the maximum of RU and RZ versus RU times RZ versus RU times RY has to be greater than 0. Basically what this means is that the utility algorithm for treatment, the R, has to match at least one of Z and Y for all W and X. It doesn't have to match both. We wouldn't expect that. But this simple assumption basically ensures that we have a rational utility in the sense that if a treatment is stronger in terms of both Y and Z than another treatment, we would take it. And this theorem says that there exists a random variable that allows us to construct the H that allows us to formulate the utility precisely as a linear utility. So this is an important result. And now I will talk a little bit about some of the assumptions that we need for this. We need the standard causal assumptions for dynamic treatment regimes, C1, C2, and C3. These include the causal consistency, SUTFA, and that sort of thing. And then it assumes positivity, meaning that it's probable that each treatment is received for all X and W. This is the propensity score of the PA given XW. And also sequential ignorability or no unmeasured confounders is required. In addition, we're going to require C4, which is that the treatment and Y and Z are independent of H, the person's preference, given X and W. So X and W has enough information to assure this independence. C1, 2, 3 are standard assumptions, as I said, in dynamic treatment regime. C4 holds automatically if the assumptions of lemma 2.1 hold. So rational utility. C4 can be weakened to allow something where we have to model pH and times Y's expectation and pH times Z's expectation, just as some dependence between H, X, and the other terms. And so under C1, C2, and C3, it can be shown that the argmax is precisely the argmax of conditional expectation given this linear utility. And this can be rewritten when we have C4 assumed. We can separate the expectation so we can model the expectation of pH separately from the expectations of Y given X, W, and A. And the advantage of that is we could just use the standard Q functions for each of those outcomes in our calculations. So this suggests a strategy, and this is the strategy that I just sort of started. We estimate the Q function, the expectation of Y given X, W, and the treatment, and we do it for both Y and the outcome Z. We postulate a latent preference model that links the unobservable H with X. This gives us a model of the expectation of phi of H given X and W. And then we plug in estimators based on estimates obtained from that to get our optimal treatment rule. In our discussion of this in the Butler et al. Paper, we just used a linear regression model for Q with all the important interactions for the treatment, tailoring variable interactions. And our unknown parameters are grouped as psi W and psi Y, the parts related to the item response outcomes as well as other terms. I'm sorry, psi Y and psi Z, that's a typo. It should be, those are the parameters for each of the different Q functions. And we use linear least squares for that and construct an estimator of the Q functions by plugging in those estimators. Now, we're going to assume that H is independent of X given W. In other words, there's enough information in the item response that we don't need additional information from X to get at H. And this simplifies our discussion, allows us to focus on a more traditional approach to item response theory. We're going to be using a Roche model. This is a generalized Roche model where we allow the slopes of the beta slopes to be very different from item to item. Let beta star be the true parameter values, and we'll use an EM algorithm to estimate beta and hat. And the idea here is that with this, we usually assume there's some fixed distribution of H, for example, standard normal, and then we specify the conditional distribution of the item likelihoods given H. And then we could study the posterior for this to get this mean using Metropolis Hastings. Turns out, though, that something that's just as accurate as Metropolis Hastings is a method of moments estimator, which we use instead, which involves solving a simple estimating equation given here. And then once we have that we plug in, once we solve that for H, we plug in that to get into the phi function, and we get our estimate. And then we estimate the dynamic treatment regime by taking the weighted combination using this mu hat for our weights of Q hat and Z hat, and we optimize based on X and W. Okay, and so some assumptions for our theoretical results to obtain. We need, first, we're going to assume that HW is the explicit solution to the true, plugging in the true beta stars. And we need to have that the W number of items is at least 3, but it could be as large as order e to the n. So it can be exponentially large approximately. And that's useful because we'll be going to we're using item response theory later on, and we need that potentially growing number of items. The estimator is consistent for H star W, and we have in our paper some sufficient conditions for that to work. And the estimator is obtained from our regression models for the Q functions we also assume are consistent. Okay, so the first theoretical result established consistency of the DTR when the sample size diverges but the number of items fixed. So this will the goal is to get the optimal treatment for the items we actually have, the finite items we have. And we can prove that this procedure will lead to asymptotically consistent. The value function will be asymptotically consistent and match the true optimal this dynamic treatment regime in that situation. Second result says that if we're able to let the number of items grow and they satisfy the positive slope assumption for the Roche model, then we will actually not only get the optimal treatment, but we'll get the oracle treatment that's as if we actually knew the patient preference H precisely. Let's look briefly at an application of this to the CATIE study. This is clinical antipsychotic trials of intervention effectiveness. It's a schizophrenia trial. It was designed to compare new antipsychotic drugs to conventional ones. It was a randomized controlled double-blind multi-phase trial. Trial targeted patients already being treated for schizophrenia, but who might benefit from a change in their treatment, their medicine. Patients receiving antipsychotic treatments and were also offered psychosocial treatment with their families. Everybody had the opportunity to receive that. There are several phases of the study. We're just going to use the first phase. In this phase of the randomized study, there were 4 atypical antipsychotics, and one conventional antipsychotic, perfenazine. And for ease of exposition, we're going to dichotomize the treatments into these 2 groups, and we'll show later that that actually makes sense. At baseline, patients answered a 10-question binary response. We only used 9 because the 10th one was not relevant in terms of evaluating whether they preferred efficacy versus side effect burden. And that's our focus here. And we use comes from a validated instrument called the PANSS. And side effect burden measured as a sum of side effect and adverse event indicators together. So we examined the effect of the 2 Q functions, one for efficacy and one for side effect burden. And we find that the signs of the treatment component are actually different. They're different between these. One's positive, one's negative, as well as several important interactions. This suggests that if both of these outcomes are of importance, neither one of these Q functions alone could probably reflect what a patient really desires in terms of their overall outcome. And in fact, when we estimate this, we find that that's true. If we estimate pi y hat, which focuses just on efficacy, we get that the atypical antipsychotics, which are considered stronger than perfenazine, are prescribed more often. If we focus on side effect burden alone, we get the opposite, more perfenazine, which has a milder side effects but less of the atypical. If we use the patient preference questionnaire based on their answer to the item, we actually get a mix of these 2, which shows that in this case, it appears to be that it's informative to use this approach. So just a discussion to give a high-level summary of this. So, and a few other comments. An alternative item response theory-based patient preference elicitation is discrete choice modeling. I want to mention right here that there's something in the United States called the HEAL Initiative, which is a very, very large NIH effort at reducing opioid dependency and other issues that relate to opioid treatments. And there is a sub-project in there called the Backpack, which is still a large study. It's hundreds of millions of dollars. There are many, many sites and centers involved. Our UNC is the coordinating center for the joint randomized trial, which will be a smart design, sequential multiple assignment randomized trial with 2 randomizations. And there'll be 4 initial treatments and multiple augmentations and alternative treatments, second stage. Moreover, this approach of balancing utility functions will be the second aim. Primary aim is to optimize treatments that decrease pain as much as possible. And then we'll combine that in the second aim using patient preferences in this manner, elicitation, to look at ways of combining, according to patient preferences, pain and functionality and fatigue and other outcomes. And so that's in the works. That trial has been formally reviewed, and the funding has been approved, and it has been voted by the steering committee to go forward. And so we're now preparing for launching this, but it will take several more months before it will be launched. It'll involve 630 patients. And so going back to this study, so we'll be using discrete choice in that case because there are 7 attributes, not just 2, and that's a little more efficient for measuring the relative utilities or relative priorities for patients of those 7 outcomes. Another important aspect is calibrating the patient preference latent construct for accurate utility estimation. Once we have that construct, it hasn't been validated using treatment, and so one needs to have an additional validation stage and calibration stage to make sure that the actual outcome they get matches what they preferred. And there's a few other methods for incorporating multiple outcomes into precision medicine that have been proposed under a variety of contexts. The literature in this area is small. And an interesting extension is to the multi-decision setting, which I just mentioned, and which will be applied to the backpack. And this is very challenging because patient preferences may also change over time. Okay, so that's the first idea. The second idea is quite different. It's still the idea of multiple outcomes, balancing them, but this time we want to look at physician decision-making. And clinical decision-making often requires balancing trade-offs between multiple outcomes. Can we learn from observational data how clinicians are trying to balance competing outcomes and help them improve on their decision-making? Well, one approach would be if we knew the clinicians were doing it correctly all the time, we could just use standard inverse reinforcement learning approach. And based on the outcomes combined with the decisions that are actually made, we can look at how the experts are making decisions, and that could tell us how to weight the various utilities. However, in human medicine, it's more likely that they do that with error. And so we approach this problem assuming that there is maybe error involved in the process. And this is a paper in press with JMLR currently, Luckett, Labor, Kim, and Kosrock. And the example that we want to look at here is bipolar disorder, where if we treat depression, it could induce mania. And this is a serious issue. So we'll actually look at some bipolar data a little bit later. In this case, the data is a little bit less complex than before. We don't have the items because now we're looking at the decision-making process itself to learn how to weight these outcomes. But we do have tailoring variables, X. We have the 2 treatments, again for simplicity, just 2. And then we have 2 outcomes, again for simplicity, just 2. We need the standard dynamic treatment regime assumptions, consistency, positivity, ignorability. We will also need some identifiability assumptions. I won't go into detail about those, but they're important as well. I'll give a little bit of that a little bit later. So we have our Q functions from before. Now these only involve X and the treatment A, tailoring variables. And this is a little bit more of the standard dynamic treatment regime. If we have those Q functions, the dynamic treatment regime is just the argmax of the Q for a given value of X over A. And in general, these rules would not be equal. They could be antagonistic effects. As we mentioned, this was the case in the schizophrenia study we mentioned earlier. And it's very likely, guaranteed to be the case with bipolar disorder when treating depression. And if both Y and Z are clinical relevant, of course, can't use either one of these. We have to do something that combines them. And so we're just recapitulating some of the ideas we mentioned before. We want to construct a utility function, Y and Z, that combines these, and we want to look at physicians' decisions to help guide us. And so the goal is to get the Q function based on the actual utility that physicians are trying to use. And then the optimal regime would be based on that Q function. And we mentioned that we can use the fact that that if they're rational utilities, we can use a convex combination. So that's what we're going to assume here again. If I just want to go to the middle bullet here, if we knew that the physicians could do it perfectly, we really wouldn't need to go through this complicated model. We could use more traditional inverse reinforcement learning and just figure it out and train them well. I have clinicians trained well, so they just do it right all the time. However, human medicine is very, very complex. Now, what we're going to assume first is that they can make error. mistake. And so we're going to assume that the probability that they get the right treatment to the person according to the true, correct, optimal utility, that will be a logistic model, will be the model given the covariates X. And beta is the unknown parameter. It could be a probit model, but this is the one we're using now. And let's assume initially for simplicity that the utility function is just a fixed constant linear combination, that there's just one fixed one, but we don't know what it is, but we know it's just this simple convex combination. And we already mentioned that we know that a linear combination is sufficient for rational utility, but what we're assuming now is a little stronger than that it's a fixed weight. And this would define the Q function to be omega. And it turns out because of the linearity of the Q functions, it's just going to be the weighted combination of the Q functions. And that would, if we knew that omega, then we would be able to take the argmax of that with that fixed mega plugged in and estimates from of the QI and QZ, for example. And so we're going to use plug-in estimators based on regression models, as we described before. These could be a variety of choices. And we'll talk about that a little bit later. We're going to, for a fixed value of omega, we can plug in omega to get an estimate of the Q function for the utility under omega, but we don't know what omega is, but we're going to plug it in there. Now, let's look at the joint distribution of our data. It includes the conditional distribution of y and z given x and a. It includes the probability of a given x, and it includes the distribution of the x feature variables. And we can factor this out. If we assume the first two terms do not involve omega or beta at all in the parameters, we can pull out a likelihood and we get a relatively straightforward likelihood. Of course, we don't know the value of d opt omega, so we have to plug in estimates that depend on omega. And so the idea would be we plug in those estimates, we optimize this likelihood over both beta and omega to get the estimator. And that would be the dynamic treatment regime. The Q function using this weighted combination would be the estimate of the optimal treatment rule. Now, a couple things about estimation. This is not a standard, it's not a smooth likelihood. So gradient-based approaches won't work. For a given value of omega, it's straightforward to compute the profile estimator. So we could just do a grid search over omega. And that's what we propose doing. And then beta hat is the one that corresponds to omega that maximizes the profile likelihood. Now, in many applications, it's very realistic to expect that this domain preference could vary widely across patients, especially with schizophrenia. And so we want to extend this idea to allow the weights to be functions of the patient's characteristics and unknown parameter theta. Here, we again use a logistic model. It could be a probit, it could be something else. But that's what we use as the weight. So it's for the purpose of this as a weight. So this is different than the logistic regression. But the first model is the error, the chances of getting the probability of getting it correct. And this is the weighting that's used. And so this is what we actually want to know, because this will allow us to know, once we know that, we can actually estimate the dynamic treatment regime. Okay, so here we have to plug in the estimates for Q hat again and the W of theta, and then we have to maximize that sort of pseudo likelihood, but this time over theta and beta. This is much harder than before because theta could be high dimensional and a grid search is not going to work very well. We've tried it, doesn't work very well. What we'll do is use a Markov Metropolis-Hastings algorithm that works quite well. And we're able to get the maximizer well, and that's how we'll estimate the theta and beta. We'll use the profile likelihood and the Metropolis-Hastings to get the best theta, and then the beta that goes with that will be our estimator. And so we'll assume, I already mentioned this assumption, this is a logistic model, and the utility has this form. Now, here's the additional identifiability condition we need. And there's a few other minor details to this, but the basics is that for X almost surely, if d theta naught opt is equal to some other d theta, then theta has to be theta naught. In other words, you can't have two utility functions that match the optimal with different thetas. And the main theoretical results rely on a number of additional assumptions. The rate of convergence for the estimated Q functions, we're going to assume root n right now, which could be satisfied with linear or generalized linear models. and the positive probability of patients with X values near the boundary. In other words, we have to have a non-zero density near the boundary where the decision rule is true. A lot of interesting things happen on the boundary. If we don't do that, we sometimes get results that are trivial, where you get the right answer almost surely with not any with no variability at some for n large enough. But under the conditions that we stated, you get a non-trivial limit. Under these conditions, the square root of n of theta n hat minus theta naught and beta n hat minus theta naught has this unusual limiting distribution, which is a smooth functional. Well, it's a smooth functional of, but complex functional of a vector of Gaussian random variables. And this is, and we also are able to develop a semi-parametric bootstrap that allows us to estimate this distribution consistently, asymptotically. Some of the theory that we needed to do this involves some fairly non-trivial empirical process techniques using the argmax theorem. And also we had to use something for functional analysis to develop a little refinement. And the basic conclusion of this theorem is that within a compact set, if we have a subset where we have unique maximum, as we approach functions that approach that within this bigger set F, as they get closer to that, they begin to get asymptotically unique maximum as well. This is known to there's known counterexamples when we don't have a compact set here. However, we're able to show that a compact set that's relevant to us allows us to do this, and we're able to get this result. Here's a high-level idea of the theorem. It basically says that we have a way of estimating Monte Carlo-wise and make repeated draws of the limiting distribution. So just want to mention a little bit about how this is applied to some data. I mentioned I mentioned the data about the bipolar disorder, and there's a study, the STEP BD SCP study published in New England Journal of Medicine, and there was an observational component to that study of 1,437 patients that's suitable for us. Here, we'll use Y as depression and Z as mania outcomes. And our goal is to help the physician know when to treat or not treat depression. That's a slight simplification of the real questions of interest, but it's pretty close to what's important to them. We're able to estimate this well and show that and estimate the optimal rule. And then we're able to test using our limiting distribution and obtain statistical significance that this would lead to a 7% improvement in outcome, statistically significantly. And then if we switch our two to and it turns out that increased age and history of substance abuse were important factors in the weighting of the two outcomes, which were depression and mania. Now, if we change the two outcomes to depression and side effect burden, we also get an improvement, but this time of 9%, and it's also statistically significant. And there are some important other things to think about here. We can estimate patient utilities if we assume that the clinicians make treatment decisions with a goal of maximizing each patient's utility. Accounting for patient-specific utilities can improve outcomes over standard of care. I also want to mention something is that you'll notice that there's actually 3 outcomes that are probably of real interest: depression, mania, and side effect burden. So ideally, we'd want to do this across 3 outcomes, not 2. And so we do have some ideas of extensions in that direction. And simulation suggests the method's robust utility model misspecification. We tried to have several model misspecifications. Of course, if we go far enough, it breaks the approach, but it works pretty resiliently, surprisingly. The approach can be extended to multiple decision times, more than 2 outcomes, and more than 2 possible treatments, as I mentioned. A Bayesian approach could potentially be developed to handle the non-smooth pseudo-likelihood. And so that's all. So thank you for your time.
Thank you, Michael. And it's a great talk. And any questions from the audience? If any questions, you can ask. Okay. If no questions, we'll go to the next speaker. And actually, our next speaker is Professor Susan Murphy.
Excuse me, Professor.
Huh?
Here is a question. It's a pleasure to be with you all.
And make the informality less necessary. Those policies are like reducing heavy.
Somebody has questions?
Yeah.
Okay.
Ease of the text, reducing the cost and the ease.
Hey, I have a question for Dr. Khosrow.
Associated with,
Yes.
So I think your work, especially the second one, to me is kind of similar to inverse reinforcement learning.
Yes.
Because the target of reinforcement learning is to estimate the reward function, I think, which is the utility function here. So I was wondering if this kind of problem can be solved by some existing IO methods, or can you discuss a little bit about the difference between your methods and some classic IO methods?
Yeah, that's a good question. Now, I will admit that I only know a little bit about inverse, about the literature, the full literature, but I know some. My understanding is that what's new in our work here is we're allowing the decision to be made with error, and we don't know which decisions are correct in advance. Does that make sense? And I think that normally with inverse reinforcement learning, you have to have that you believe the outcomes are the experts are making the right decision. You just don't know how they're weighting priorities. And in this case, we're allowing error to creep in there. And we're also using a model that a class of models combination built up from models that are fairly useful to apply in human health settings like this.
Okay, thank you.
Thank you. Now we
No more
can-
questions? And okay. And I think I'm going to introduce the Susan. And actually, Professor Susan Murphy and cannot attend this conference, but she recorded her videos. And let me introduce Susan first. Professor Susan Murphy is a professor of statistics at Harvard University, and is Radcliffe and alumni professor at Radcliffe Institute, Harvard University, and professor of the computer science at the Harvard John A. Paulson School of the Engineer and Applied Sciences. Her lab works on the clinical trials design and on online learning algorithms for developing personalized mobile health interventions. She is the 2013 MacArthur Fellow and a member of the National Academy of Science and the National Academy of the Medicine and both of the United U.S. National Academies. She's the current president. She was the current president of the IMS, And thank you. And I think Danda, you can play her video now.
It's a pleasure to be with you, all of you today. And at this, being able to present at this conference, Statistical Learning Methods in Modern AI. Today, I'm going to talk about some work that we just started, and it's about how you think about the data you obtain once you've run an online decision-making algorithm, such as a reinforcement learning algorithm. And we'll do this in the context of digital health, in particular with heart steps. This is a physical activity intervention that's delivered via the smartphone and uses sensors on a wristband tracker. Where the study's over, we ran this algorithm, and now we're asking, well, did this algorithm, this online decision-making algorithm, did it personalize treatment? Could we potentially overpromise what it's done? I'm fortunate to have many collaborators. These types of studies do involve large interdisciplinary teams. In particular, though, I want to put a shout out for Peng Liao. He's a postdoc in my lab in statistics, Kelly Zhang, who's a PhD student in computer science, and Zhe-Yang Shi, who is an incoming first-year Harvard PhD student in statistics. All of them have worked on this project. So we're going to start off with a discussion of hard steps, the study that motivated this work. So this is, as I said, it's a coach. It's a mobile intervention. It's intended to be a coach for individuals who have or at high-risk coronary artery disease, in particular people with stage 1 hypertension, high blood pressure. And it involved 3 studies. All 3 studies are over now. The first was for 6 weeks, and the second 2, which are highlighted in blue at the bottom of the slide, were for 3 months and 9 months. These are what I call micro-randomized studies. This should become clear what that means as we go along. And in particular, the second 2 studies that merged together were personalized, and that should also become clear. So this activity coach includes a lot of different treatment components. We're going to focus on only one, the one that we used, the decision-making algorithm. And this is whether or not to send a contextually tailored activity suggestion. That is, it's a binary action, send the suggestion versus not. The content of the suggestion is tailored to the current sensor data. And you can see that here with this example. What happens is the phone would light up, the phone would ping, and you would get a message like this. And this message came in the morning on a work day when it was pretty cold. And so you can see how the message tries to frame that and just tries to get the individual to walk a little bit more than usual. It could occur, delivering or not delivering a message can occur at any of 5 times a day, and these are user-specific times related to that individual's, the way they conduct their life. The reward, that is the outcome, is the 30-minute step count following each of these 5 time points. And the reason why it's over such a short period of time is because these activity suggestions are highly tailored to the context that individual is in at that moment in time. And they're intended to be used at that moment. So after the study's over, one sees data that looks like this. So on each user, you get these tuples, state, action, reward for some duration of time, depending on whether they're in the 3-month or the 9-month study. State is, or context is, it's composed of the sensor data that's being accruing from the tracker, and also sensor data from the phone, and adherence and so on. And then A denotes action, and that's the binary, deliver a suggestion versus don't deliver a suggestion. And we're going to talk about the algorithm that ran during the conduct of this study to produce A, capital A, deliver versus not, the binary action. And then subsequent to that, after that is the reward. And this is, in our case, it's the log of the 30-minute step count. These are highly skewed. Step counts are skewed data, and so the log is used. At the very bottom of the slide, I have just a small amount of notation, and we're going to use this repeatedly throughout this talk. That is the expected reward, expected log step count, expected reward given current state, and action is denoted by this lowercase r function. It's a reward function. Okay, so we ran an online decision-making algorithm. In particular, it was a type of a bandit algorithm. So it's a very special type of reinforcement learning. And the idea was to personalize treatment or delivering a suggestion, activity suggestion, versus not. So based on that individual's current state, should you deliver versus should you not? And the idea here is to select these actions, binary actions, with the goal of maximizing the sum of the 30-minute step counts over the entire duration. Now, this is subject to a lot of constraints, and these constraints in the end mean that although we're interested in reducing regret, regret minimization is not the goal in these kinds of studies. In particular, we want to be able to facilitate off-policy learning after data collection ceases. This will be critical. There's a wide variety of collaborators, and one has each one has a different type of analysis they would like to do after the study is over. There's also, from a scientific perspective, there's real problems with user burden and habituation. If you send too many messages, people become overburdened. They start to ignore the suggestions, and they may even delete the app. So in the second two studies, V2 and V3, that's the 3-month and the 9-month study, we used a generalization of a Thompson sampling algorithm to personalize action selection. We generalize this algorithm in a number of ways. I'm going to only talk to you about a couple in the next couple of slides. And the reason why I'm doing that is because I really want to get to the part about how do you analyze this? How do you think after the study's over? So again, we used an online Thompson sampling bandit algorithm, or generalization of that, to decide to choose AT equal 1 or AT equal 0. AT equal 1 means the suggestion is delivered, 0, it's not delivered. This is greedy. These algorithms are greedy in the sense that they only pay attention they only attempt to try and improve the reward, the immediate reward. They don't look into the future. They don't use predictions of the future and try to take into account future, say, burden and so on. In the actual algorithm, we did alter the reward to do a little bit of that, but here I won't talk about that aspect of the algorithm. This is an online personalization algorithm because the chance that an individual is delivered a suggestion depends on the accruing evidence of whether or not that suggestion is worth it in that individual's current state. So in these decision-making algorithms, there's always two elements. There's a learning algorithm, and all that is an incremental statistical method, some incremental method that you update as data accrues. In our case, what we used is a Bayesian linear regression, as a very simple form of a Gaussian process model for this reward function. And then the second element of these algorithms, these online decision-making algorithms, is the action selection strategy. So what strategy is one doing to experiment and be able to learn whether to send a suggestion? And what we're doing here is posterior sampling. So it matches the learning algorithm. In particular, we calculate the posterior probability that the treatment effect in the user's current context S is greater than 0. And then we take that probability and randomize the user, the individual, to getting a suggestion with that probability, that posterior probability. So this is called posterior sampling. Some points about how we developed this algorithm, the bandit algorithm. First is we use, as I said earlier, we used a Bayesian linear regression. In particular, the linear regression was for the treatment effect. So we have a low dimensional linear regression for the effect. That's this is the expected reward under send a suggestion minus the expected reward under not send a suggestion in the current state S. We modeled that via this linear combination. Theta is 5-dimensional, and you'll see what the features are on a subsequent slide. And we used an informative prior, and in general, that's how we are using reinforcement learning algorithms, is we use a Bayesian mindset and informative priors. And in our case, the informative prior comes from the first HeartStep study. And it's a Gaussian prior for the theta weights, the 5-dimensional theta vector. And in particular, the one thing I want to say here is the prior mean for all the weights is 0 except for the first weight, the first entry in theta, and that's positive. And this is going to be important as this is going to come into play later on in this talk. The action selection strategy, as I said, it's posterior sampling. Now, it turns out one has to give some thought to posterior sampling. It's not just a black, you just don't use it. And we realized this after we had started the study, and we had to restart the study. We had to adjust the algorithm and restart the study with new participants as a result of this realization. So I'm going to describe that to you here. So with posterior sampling, you send a suggestion A = 1 with probability P, and this P is the posterior probability that the treatment effect in the current state is greater than 0. The question is this a good idea? So you see the first item 1 is in some states, this posterior, it's a Gaussian distribution, maybe it will be really peaked around 0. What that means is this posterior probability will average at 0.5. Is this a good idea? Do you want a probability that averages around 0.5 when the learning algorithm is indicating there's no effect of sending a suggestion? In some states, so number 2, in some states, what we'll see is this posterior distribution of the treatment effect will be very peaked and will center around a mean much greater than 0. And so then the posterior probability is going to be really close to 1. Is this a good idea? Is it a good idea to always send the suggestion in that state, or to nearly always send that suggestion in that state? Well, neither one are good ideas. And in addition, we need to permit off-policy learning after the data collection. It ceases after the study's over. You facilitate this by preventing the posterior probabilities, in particular, the randomization probabilities, from getting too close to 0 or 1. And so you see this little graph, this little blue graph that I drew into this slide. So what we did was the x-axis is the old probability, the y-axis is the new probability. And if the posterior probability, the treatment effect is greater than 0, is greater than 0.8, we use 0.8. If it's lower than 0.2, we use 0.2, and then we have a linear interpolation in between. And it turns out that both that lower bound in the case of heart steps 0.8, and the upper bound was 0.8 and the lower bound was 0.2 in heart steps. These are determined. These can you want to be able to do off-policy learning, so that facilitates that. They're not too close to 0, but from a scientific perspective, these are determined using considerations of habituation and burden. And we were able to we have a discussion with the domain scientists, and they tell us, well, only 20% of the time do I want this suggestion to be sent if at this time there's no evidence that the suggestion is effective. Okay, as I said, we changed this banded algorithm in a number of other ways, but I really do want to get to this third bullet point. After the study's over, it's very easy to look at some of the data and to think that this algorithm is fantastic and it's personalizing. And as statisticians, we have to ask, is this spurious? So in general, and in heart steps, this generalization of the banded algorithm was run online separately on each of the N users, N = 91 in this particular setting. And here's some first questions that I might want to ask. So I have the data in front of me, the study's over. Is there some evidence of an average across all individuals, a treatment effect on the 30-minute step count? That's a natural first question. A second one is there heterogeneity in the treatment effect? Was it really a great idea that I ran this banded algorithm separately on every person, and thus I had to accommodate that heterogeneity? So how are we going to think about those questions, addressing those questions? So what we did, we couldn't find, there's really no work at this time. This is an area that's very new. And there wasn't any existing work in the statistical community or in the CS community, machine learning, to how to think about this. And what we did was we went back to classical clinical trials, very old, from last century, and we use meta-analysis. So meta-analysis is different from meta-learning, okay? It has some similarities, but it's different. So I give you a reference at the very bottom of this slide. You can see the references from 99. That tells you how old this literature is. And in this case, what happens in that setting, in meta-analysis and classical clinical trials, what one is doing is you have multiple clinical trials with the same, usually a drug, being tested, and you want to combine results across those clinical trials. So here in our setting, we're going to view each user as a clinical trial. Each user will have their unknown vector, 5-dimensional vector of treatment effect coefficients. That's and it's unknown, it's the true vector. That's why it has a subscript of 0 on that slide. And we're going to estimate that vector for each user by their posterior mean. And as we know, we're in a Gaussian setting with a Gaussian prior. This is the same as estimating the unknown vector by a ridge regression estimator, L2 penalization. Now, in classical meta-analysis, there's 2 ways that people think about these problems. The first way is you're only interested in the 91 clinical trials, in our case, users in front of us. We're going to only make comments about these users. And what one does then is one assumes this ridge regression estimator over either 450 time points or even more, to over 1,000 time points, has an approximate normal distribution where the mean of that distribution is the true that user's treatment effect coefficient, and some variance covariance matrix. This actually makes good sense in this setting. Remember, the bandit algorithm that we're running is not a regret minimizer. It just attempts to reduce regret. So you always have some exploration. The randomization probabilities are always between 0.2 and 0.8. A second way to think is think more broadly. These 91 users, these N users, are a sample from some larger population. And in this case, this made a lot of sense because this study was run at Kaiser in Seattle in northwestern United States. And this is a large healthcare organization, and people were recruited when they were first diagnosed with stage 1 hypertension. So if Kaiser wants to make wants to use an app of this type for its newly diagnosed patients, this would be the population we'd be interested in. In this case, you think more of a random effects type of point of view, and in particular, each user's 5-dimensional treatment effect coefficient is a sample from some overall population. The overall population has some mean, 5-dimensional mean, and some variance, user-to-user variance. Okay, so we started to the first question. So this question is about population inference. So this is about the larger group of people with stage 1 hypertension. And in classical, we just use the ideas straight from classical meta-analysis. And in particular, what one does is one gets a weighted average of each user's treatment effect coefficient. So this little e, this is a vector with 1 and 1 entry and 0 everywhere else. It's one hot vector. And all it's doing is it's picking out each feature in turn. And the features are listed in that green table. So there's 5 features, their overall action, and then the interaction terms. The current context was what was there, was it prior dosage, was exponentially discounted number of suggestions that have been sent recently over the past week. Engagement, whether or not the user was working with, was looking at the app all of their own volition. Location, is the user in a structured environment currently or a less structured environment? And step variation, how variable their activity has been around that time over the prior week. So again, each one of these estimators is a weighted estimator of the individual specific coefficients. And these weights are, the weights are just from the variance components. And this is, like I said, it's classical meta-analysis. And you see from the table from the first row that indeed there does appear to be some positive effect, increasing step count when you send a suggestion versus not. That's great. But when you go to the second row, you realize this is not, you have to be very careful when you make the prior statement, because if the coefficient for dosage interaction is negative and highly so. And indeed, what that means is that if the individual has had any very much dosage, very much recent number of suggestions, there doesn't appear to be effect on their step count. This is very depressing. And this emphasizes it even more fully. So let's say the user is in this particular state. They've experienced their recent dosages at the average level. They're currently engaged. They're looking at the app. They're at home or work structure. That's a structured environment. And their recent variability and activity is low. Then you can use this weighted average and form a confidence interval. And you see, indeed, the data does not provide a lot of evidence for there being an overall average effect across all users of sending a suggestion versus not. So now we're going to look at treatment effect heterogeneity. Is the better action user specific? And in classical meta-analysis, what one generally does is switches to the finite sample. We're just looking at these 91 users. Is there evidence that among these 91 users, there's differences in effects? So what we do here, and again, this comes straight out of that literature, that tutorial that I showed you earlier. We take each user's treatment effect and we subtract from that an average treatment effect. So each user's treatment effect, the average, and we get the variation. The average is a weighted average, weighted by the within user variance. One compares this to a chi-squared on n-1 degrees of freedom. And here you see the results. But of course, let me just remind you, the null hypothesis is there's no treatment effect heterogeneity. That is, this coefficient of weights, the 5-dimensional coefficient of weights, it's equal for all 91 users. When you go to that green table, you see, indeed, there's a good bit of evidence that the treatment effect there's a lot of treatment effect heterogeneity. I was pretty surprised at this, to be honest. So here's a natural question, if you're familiar with the field of reinforcement learning, is on average, does the banded algorithm, this generalization of a banded algorithm, select more effective actions than if we just used the prior distribution and formulated a the policy for choosing decisions? So to understand what I mean by more effective, first I'm going to define the average reward. So the average reward for a policy on user I is denoted by this V sub I. Pi is the policy. So the policy can be from the prior. The prior can be used to produce a policy. And you see that it's expected average reward for that user. This expectation is an average over that user's states, the states that user experiences, as well as any stochasticity in the policy. And the policy derived from the prior is a stochastic policy because you use prior probabilities to decide whether or not to send a suggestion or not in a given state. Now, the estimator of the user I's average reward under the banded algorithm, here we got to recognize the banded algorithm is learning. So it has a different probability of sending a suggestion as time goes on, even if the individual were in the exact same state. So, but it doesn't matter because all we need to do is take the average of the rewards we see in front of us for this user. And then to estimate the average reward under the prior policy, we use importance weights. More sophisticated estimators have been developed for this setting, but here we kept it very simple. So we didn't use, for example, a doubly robust estimator. We just used importance weights. Okay, so now we put it in our meta-analysis setting. So each user's theta, now it's a scalar theta, is the comparison of the value under the bandit algorithm minus the value, the average reward under the policy formed from the prior. We don't observe theta sub 0i. Instead, we estimate it by the difference between the estimated values. In our setting, because we are continually exploring the randomization probability state between 0.2 and 0.8, this theta hat we can approximate with a normal distribution. So if we focus just on the 91 users, that's what we'll do. If we want to have something, if we want to make a statement about overall, the entire population of individuals with stage 1, newly diagnosed stage 1 hypertension, then we additionally make that second assumption, that the true scalar difference in values varies normally across the population. Okay, so the first question in this particular set is, does the bandit algorithm result in higher rewards than the prior? So this is on average across the entire population. And indeed we see, yes, it does. We get an average higher performance. And this is thought to be the case because the bandit algorithm doesn't overtreat. Remember when I discussed the prior, I said that the first entry in the prior means was the prior mean was positive, because on the original heart step study, we did see a strong effect of treatment, sending a suggestion. So the prior essentially sends too many suggestions, and the bandit algorithm backed off on that. Also, if we start to look at treatment effect heterogeneity, so does the difference in values, is it the case that for some users it's really worth running that bandit, and for other users it just doesn't matter? And indeed here, that's that lower table, you get gross heterogeneity, indicating that for some users really appear to have benefited from running the bandit algorithm. So I have 2 more questions. These are more exploratory. On average across users, does it appear that this algorithm learned over time? Now, our prior was an informative prior, and our prior stated that the treatment effect of sending a suggestion versus not is positive. And we already saw from our analyses that the data does not indicate that that's the case, that the treatment effect on average across all users is positive. So what we're expecting here is we want to see, well, did the algorithm learn this fast? On average across users, did the algorithm quickly learn that there's really actually on average no treatment effect? Okay, so to do this, we use a bootstrap procedure. So the first thing is this blue curve that you're seeing, in particular if you focus on the graph on the left-hand side. This is the actual data from the study. It's the average posterior mean of the treatment effect in a particular state, and the state is given to you in the second bullet point. So what we see, if you can see it, the blue curve starts around 0.47. That's that prior mean of the overall effect. And then it goes down pretty rapidly across time. Now you could ask, is that rapid decrease just noise? So to think about that, we ran these bootstrap experiments. So there's 2,000 black curves, each corresponding to a bootstrap trial. Okay, how did we form a bootstrap trial? So in each of the 91 users, what we did was we subtracted from their reward, we subtracted their treatment effect in the particular state they were in at that particular time to get what we call a residual. It's not mean zero because we're only subtracting the treatment effect. But for that individual, we now have state residual, state residual, state residual over the entire duration of time that individual was in the study. We then randomly sample. We obtain a bootstrap sample of 91 users, so 91 trajectories of state residual, and we run the bandit algorithm on each trajectory separately. The bandit algorithm will see a reward equal to the residual if the bandit algorithm chooses no, do not deliver. If the bandit algorithm chooses deliver the suggestion, then the bandit algorithm will see the residual plus the treatment effect, the prior mean treatment effect. So the black lines are all under the ground truth that the treatment effect is in accordance with the prior mean. Every single one of the 2,000, because there's 2,000 bootstrap trials, each of 91 users. And you see that if you look at how the performance of the posterior mean in each one of those bandit studies, they form a cloud and it gradually gets a little narrower at the end, but it pretty much stays horizontal. And very rapidly, now we see that the blue curve, the actual curve from the study, drops below that line pretty quickly, probably by time 40 or so. The earlier drop, the immediate drop, is well within the mass of black lines. And so you can't really say much about learning, say at time 20, for example. The second figure on the right-hand side is just a sanity check. If the posterior mean for each individual was the ground truth, then would the blue curve stay within the mass of the bootstrap studies? And indeed it does. Okay, so this is my last question I wanted to ask, and this actually is the reason why, this question is the reason why we actually started going down this path. And it's the reason why it emphasizes the fact that AI can be so dangerous and it's so easy to be misleading. So we had quite a number of users where when we looked at that user's data, it looked like the user was experiencing the bandit algorithm was personalizing to that user in a very interesting way. And I'm going to show you a graph of one particular user on the next slide. The question, of course, is this just spurious? I mean, remember, the algorithm itself is a stochastic algorithm. So here's a particular user. The horizontal, the x-axis is the date in study. So this user joined this study in mid-November 2019, and left the study, ended the study in early August 2020. This is in Seattle, and Seattle shut down because of the pandemic around March, late March. So you can see this spans that entire period, pre the pandemic shutdown to post the pandemic shutdown. The dots are each dot is the posterior mean of the treatment effect in that individual's current state, divided by the posterior standard deviation of the treatment effect in that individual's current state. And why am I looking at this ratio? Because this ratio translates directly into the randomization probabilities. The higher the ratio, the higher the probability the user is sent a suggestion. The lower the ratio, the lower the probability the individual is sent a suggestion. So you can see each dot, and you see the line, the horizontal line 0. So there are many times in which the algorithm is not seeing any evidence that there's currently going to be a treatment effect. Okay, so there's two colors for the dots. The blue dots are when the individual has been looking at the app without us prompting them. The red dots, that's the engaged state. The less engaged state is the red dot, and that's when the individual just hasn't been looking at the app at all recently, in on the prior day in particular. So if you look at this, you begin to, the immediate thing, like if I show this to a collaborator, they're going to say, whoa, this is the fact that the blue dots are almost always above the red dots means that we really should be sending a suggestion only when the user is already has been engaging with the app anyway of their own volition. And you ask, the question to ask is this spurious? Is this a spurious conclusion? So what we did was we did another bootstrap study. So the blue curve is, again, is the actual data. It's the user's posterior mean for the effective engagement as the study progresses. So you can see the blue curve. So now the blue curve starts at 0 because the prior mean for engagement, effective engagement was 0. So that's why the blue curve starts at 0. And then you can see it moving through time. Each of the 2000 black curves is a bootstrap version of that particular user. And the way we get a bootstrap version of that user is we take that user's state residual trajectory, and we bootstrap the residuals. And then we run the bandit algorithm on the resulting pairs. So now it's the resulting pairs now is state, a new residual, a bootstrap residual, state, a bootstrap residual, state, a bootstrap residual, and we run the bandit algorithm. And if the algorithm says send a suggestion, we add back in the posterior treatment effect at that time, except we ensure that we set the coefficient of engagement to 0. Okay, so if you look at this, at the beginning of the study, even though it was very tempting to conclude that one should only send these suggestions when the individual is engaged because that's when they're most responsive, the blue curve is well within the mass of the black curves. Maybe at the end, like in June of 2020, the blue curve starts to drift above the mass of the black curves, indicating that indeed, perhaps there is evidence that, so this is this period of time right in here, that there's sufficient evidence that it's better to send it, it's more effective to send the suggestion in the state of when the individual, the user is engaged. Okay, this is my last slide. We used a sequential decision-making algorithm, but did we achieve personalized digital health? Here we assumed that each user is a classical bandit environment. By that I meant their states are not affected by prior treatment. And that's probably not true. But even if you are willing or you're comfortable assuming that, how would you do a better job assessing whether or not personalization occurred? There's just not a lot out there to do this. This is a completely open area of statistics. If the bandit environment is violated, say we have in fact a Markov process, how do you assess personalization in that setting? We don't know. How do we do this? Okay, thanks so much. Thanks for joining me for these 40 minutes. It would be great to hear from you. Take care. Enjoy the conference. Bye.
Okay, and I think thanks Professor Susan Murphy for this wonderful talks. I think we learn a lot from her talk. I think our third speaker today is Professor Rui Song from the NC State. And Professor Rui Song is the professor of statistics at the Department of Statistics at the NC State. And her current research, let me Interests include machine learning, causal inference, precision health, financial economics, and her research has been continuously supported as a zoned PI by National Science Foundation. She received a prestigious NSF Faculty Earlier Career Developmental Award in 2016. She is the fellow of the SA and the MS. She published around 80 or 90 papers in top-tier journals in statistics and machine learning conferences, include Anderson Statistics and also ICML. And welcome, Ray.
Thank you, Hongtu, for your introduction. Can everyone hear me? I assume that's yes. So
Yes.
today I'm going to share some of my recent work about statistical inference of online decision making via stochastic gradient descent. So I will start from the introduction of the problem setting and the related work, then talk about our proposed algorithm and the parameter and value inference results, and then share some of the numerical studies, including real data analysis, followed by the discussion. So personalization, especially online decision making for digital health and precision medicine, like Susan and Michael's talk, are very popular recently. It also has many use in other domain areas, such as personalized recommender system, marketing, and so on. So today we're going to focus on the application of a personalized online decision making. Here is a problem setting. At each decision time point, we observe features xt, which is a p-dimensional covariates, and we choose the action. In this work, we consider binary treatment at, and receive a random reward yt. So we assume the larger value, the better. We denote the data sample as a triplet OT, include xt, at, yt at time t. So the goal is to learn a decision rule D, which maps from the covariate space to the action space that can maximize the expected reward, which is the expectation of y indexed by the decision rule D. We're interested in achieving a high cumulative reward during the learning process. So its goal is consistent with what Susan mentioned in her talk. To find the optimal decision rule, we can model the conditional reward and estimate the reward of different actions. In this work, we posit a parametric model for the conditional mean reward. So we call it mu xa at parameter beta. And we use beta 0 to denote the true value of beta. Then, in this case, the optimal decision is the function or the decision that can get the larger values of a conditional mean function. So if action 1 gives us larger mean, we say optimal decision is 1, optimal action is 1, otherwise it's 0. And we use beta hat to be an estimator of beta 0. So the estimated optimal decision is just just still the same indicator function, whereas the index parameter right now is beta hat. To achieve a high cumulative reward during the experiment, we have to make a decision based on the historical data. If we estimate beta 0 using previous sample, so we denote that as OT minus 1 bar, include the data from O1 to OT minus 1 to get beta hat T minus 1, then the estimated optimal rule is an indicator function that with the parameter estimation replaced by beta hat T minus 1, the same rule as defined before. So in this case, we can choose AT as D hat opt T minus 1 evaluated at XT to fully exploit the current learned model, hope to get a high reward. But if we take this greedy action, we may end up stuck in one suboptimal action and living with other actions unexplored due to limited sample performance. So to alleviate this problem, exploration and exploitation as two main procedures have been introduced in the literature, where exploration refers to actions that improve the model estimation, and exploitation refers to actions that can achieve a higher reward. So there's often a conflict between them because at one time you can only take one action. Many algorithms have been designed to balance exploration and exploitation. Some popular methods include upper confidence bound method, that is, the actions are taken with respect to the maximum possible mean plus its variance. And Thompson sampling was introduced in Susan's talk. That refers to we take the action according to the probability that proportional to the best to the posterior distribution, then we take this action as the optimal action. And epsilon greedy and forced sampling methods are two random sampling scheme, where epsilon greedy refers to the mechanism that at every stage we take a fixed randomization probability epsilon. And the forced sampling method refers to the mechanism that at a certain step we have at a certain pre-specified step we take a random exploration. So in this work, we focus on epsilon greedy method. That is, we select a series of exploration rate epsilon t, which is a value between 0 and 1, and choose the action according to a Bernoulli distribution with success probability 1 minus epsilon t times d hat of the t minus 1 at xt plus epsilon t over 2. That is, with probability 1 minus epsilon t, we're going to take the greedy action. That means when the greedy action takes value 1, this action will take in the Bernoulli distribution or will sample as value 1 with probability 1 minus epsilon t over 2. When the optimal greedy action is 0, then AT will take value 0 with probability 1 minus epsilon t over 2. So here's some discussion about today's goal. So the performance of online decision-making solutions have been extensively studied, but statistical inference of those methods are much less studied. In particular, we care about the parameter inference, which refers to the statistical inference of a data. It can tell us which feature in X are statistically important in choosing actions and estimating reward. So that will facilitate us to do variable selection for future study. We also care about value inference. So the value is defined as the expected reward under a given decision rule. You see this notation before? It can be estimated from the historical data, but without appropriate quantity uncertainty quantification, we're not able to do statistical inference. So we're not be able to compare different decision rules, for example. So that's why it's important to be able to carry on parameter inference and value inference in practical use. Here are some related work about contextual bandits. It was first formulated by Ujov in 1979 and then named by Lamford and John in 2008. There's a comprehensive survey by Torrey and Murphy in 2017. More recently, there's some work in terms of solving the linear bandits model using a randomized strategy called certainty equivalent with forcing. We introduced that in the previous slide. The consistency of the parameter estimator was shown in those papers. Young group and the Chervas et al., they took a simpler randomized strategy called epsilon greedy. Professor Yuhong Yang at the University of Minnesota, they study non-parametric models. And the Chervas et al. Study a general parametric model of the mean reward. They use epsilon greedy method to balance exploration and exploitation. So they gave the asymptotic distribution of the mean reward under the optimal decision rule, where the parameter inference was not provided. So our current work, this talk, is built on my previous work which we consider the contextual bandits problem with a linear reward model, and we solve it using epsilon greedy. In that paper, that's just a paper forthcoming, we show that the online ordinary least square estimator of model parameters and the in-sample inverse probability weighted value estimator are asymptotically normal. We also show that when the linear model is misspecified, the online weighted least square estimator using the inverse probability score weighting is asymptotically normal. Here is a brief recap of the algorithm proposed in that paper. So we started from a random exploration, that is with equal probability we take action 0 or 1. We do it a few times, we call it a burning period. We also pre-specify epsilon t, the exploration probability for the epsilon greedy algorithm. So after the burning period, we started to observe xt at time t, and we sample at from Bernoulli distribution with probability pi t minus 1 xt from the epsilon greedy algorithm. Then we observe yt, then we form the triplets ot equals xt, at, and yt. Then we update the beta hat t using ordinary least square or weighted least square on ot bar. Ot bar is all the history from O1 to ot. Then we update pi tx according to the epsilon greedy rule. So even though this is online decision making, we do this estimation in an offline fashion because every time we need to use ot bar, that's the data accumulated from the beginning. So this way, the computation is not efficient and it spends a lot of storage. So in this work, we're trying to do a real online estimation. That is, we will update the model estimation with one data point at a time. So in this case, we don't need to all the historical data. Stochastic gradient descent is a natural way to do online estimation because it uses one sample to evaluate the gradient and optimize the objective function at each iteration. So in this work, we're going to incorporate the idea from SGD to do online estimation for epsilon greedy algorithm. Here, a brief review for the statistical inference literature of SGD. Seminal work by Rupert and Polyak and Judiski suggested using the average SGD estimator for fast convergence, and they established the asymptotic distribution for the prediction problem. Chen et al. Proposed a plugin estimator and a batch means estimator for the asymptotic variance and prove their consistency. However, their batch means estimator may have under coverage or they may underestimate the variance because they ignore the dependence within the batch, the correlation within the batch. Fan et al. 2018 proposed a resampling method for the variance estimation. This method is theoretically valid and it may suffer from a huge computation burden because it needs to do a lot of resampling and to do SGD in each resample. So in this work, to balance the computation complexity and the efficiency, we're going to adapt a plugin method. So in order to do the parameter estimation, we need to define a loss function. So we denote this as L beta O that measures the difference between the estimated reward mu xa evaluated at beta and the true reward, the observed reward y. So given the defined loss function, we can also pre-specify a series of predetermined learning rate alpha t. So then, according to Robbins and Monroe to 1951, the updated rule of the original SGD algorithm takes the following form. So every time we update from beta hat t minus 1 and minus alpha t, the learning rate times the gradient of the loss function evaluated at beta hat t minus 1 and the OT, the current time observation. Polyak and Judiski suggested using the average of beta hat t at each time step as a final estimator to accelerate the approximation. So based on the average estimator, we can find the online decision making via SGD. That is, the estimated optimal decision rule after step T is an indicator function where beta T bar is plugged in as the parameter, index parameter. So in this work, we still use ipsum greedy to address the exploration and the exploitation dilemma. We denote the propensity score pi x as the probability of getting the recommended decision action as 1 given covariate x. And under ipsum greedy algorithm, pi tx takes the following form. That is, under the optimal greedy action, this probability taking value 1 is 1 minus ipsum t over 2. When one is optimal action. Similarly, it can be defined when 0 is optimal recommended action. So ipsum t is a predetermined exploration rate. Then the next action AT plus 1 is sampled from a Bernoulli distribution with success probability pi t xt plus 1. It sounds a direct adaptation, but right now we're going to discuss some difficulties in deriving the statistical inference. First, let's review the data-dependent structure when using SGD for online learning. With IID data, in this case, xt prime and yt prime are IID over t. So in this case, we can easily define the expected loss as in an online case because the data are IID. And we can decompose the parameter update rule as the following. That is, we minus and plus the same term, alpha t times the gradient of the expected loss evaluated at beta hat t minus 1. Other term keeps unchanged. So we mentioned that the blue term, beta hat t minus 1 minus alpha t, the times the gradient of the expected loss evaluated at beta hat t minus 1 pushes beta hat t towards the minimizer of the L beta expected loss. And the red term is some random noise with martingale structure when OT are IID over T. The Polyak and Judisky, they show that the average SGD estimator is asymptotic normal by martingale central limit theorem. Next, let's review our setting with SGD updated for online decision making. So in addition to have XT, YT, we have AT, the action. So in this case, even though XT are still independent over T, AT, the action, depend on beta bar T minus 1, the average SGD estimator. Therefore, YT, the response, depend on AT, also depend on beta bar T minus 1. So we do not have IID structure of XT, YT anymore. Therefore, we cannot have martingale structure directly from our setting in online decision making. So how do we solve those problems? So first, let's lay out two specific challenge. The first problem is that the definition of the expected loss now involves the distribution of AT, which depends on the previous stage estimated beta bar T minus 1. So this is not easy to calculate, if not feasible at all. If ipsum greedy decision changes with beta T bar, we cannot use this distribution as a distribution of A to define L beta. So to deal with this challenge, we choose the most simple fixed decision rule, that is the equal probability random decision, to define the expected loss, where we use PAR to denote the Bernoulli distribution with equal probability 1/2. And we denote the joint distribution of XAY as POR when A is from random exploration and PO pi when A is from ipsum greedy algorithm. So the second challenge is the random disturbance, the gradient of the expected loss minus the gradient evaluated at beta hat t minus 1. So the second term is also evaluated at OT, do not have the martingale structure anymore under our definition of L beta. That's because when we define the expected loss, we use a random exploration, we use equal probability of exploration. And for the collected data, the data collected under the epsilon greedy policy, so it's not the same distribution. So we propose to solve this problem by replacing the loss evaluated OT in the update rule with the inverse probability weighted gradient. That is, we're trying to push the sampling mechanism from epsilon greedy to the random sampling. So how do we achieve this? This G function is defined as a summation of two parts. The first part represents the observation when AT equals 1. Similarly, the second part is the contribution when AT equals 0. So let's discuss the first part. So we achieve this goal through important sampling. That is, for the random sampling, the sampling probability for AT equals 1 is 1/2. And in the epsilon greedy, the sampling probability for AT equals 1 is is pi t minus 1 xt. Therefore, the importance sampling ratio is 1/2 times pi t minus 1 xt. So under this defined G function, if expectation and the derivative are interchangeable, we can check that the random disturbance, the gradient of an expected loss minus G, so instead of the original L, is a martingale difference process. So now we can establish the results. So let's first review the updated algorithm. That is, we do online decision making with real online updating using SGD. So we still start from a burning period with some initial value of beta 0 and pi 0, alpha t and epsilon t needs to be pre-specified. So then we start to observe xt and sampling AT from Bernoulli distribution with probability pi t minus xt. Then we observe yt and form OT. Then we calculate the IPW gradient G defined in the previous slide. Then we update beta t hat. Instead of using L, the gradient, we're using G, IPW gradient. And then we update beta t bar, the average SGD. And then we update pi tx according to the epsilon greedy rule. So in this case, every time we're updating the IPW gradient with only the current stage observation OT instead of OT bar, all the previous data. So as I mentioned, we need to define the loss function. So in this following two examples, I'm going to illustrate how do we choose the loss function. For example, if we in the linear reward model, we can take this mu as the following linear form. When equal to 0, it takes the mean x transpose beta 0 for the first part of the parameter, and when equal to 1, it takes x transpose beta 0 and the second part of the parameter as the form. So we consider the quadratic loss in this case. So the expected loss takes the following form, and we can correspondingly write down the updated rule of beta at t with a defined G function. We can similarly define the logistic reward model when we have the response as a binary case. So in this case, we posit a logistic model for the conditional mean reward, and we consider the cross entropy loss in this case, also define the expected loss and the first derivative of the loss function, hence the G function can be defined. So in order to get some theoretical result, we need to have some assumptions. So assumption A1 ensures the interchangeability of the expectation and the derivative, which is important for building the martingale structure. And the assumption A2 commonly used in establishing the convergence of SGD. So I want to particularly mention that our convergence are with respect to beta star, the argmin of the expected loss. This beta star is not necessarily equal to beta 0, the true value, unless an appropriate loss function is chosen. A3, A2 and A3 ensure that we can find the unique minimizer of L beta by SGD. We can easily check that assumption A1 to A3 are satisfied by our linear and logistic reward examples. In fact, the most commonly seen in generalized linear models satisfy those assumptions. So having those assumptions with the help from theorem 2 of Pollack and Giudice, we can establish the asymptotic normality of the parameter estimator beta t bar. So from the following results, you can see that we do have a asymptotic normal with the sandwich form as asymptotic variance. And this variance term depends on epsilon infinity, which is the limit of the exploration rate in the denominator. Therefore, this pi star x cannot be 0. That means this epsilon infinity cannot be 0 because it's in the denominator. I also want to mention that even though the learning rate alpha t is not in the asymptotic variance, it doesn't mean it does not play a role in the non-asymptotic analysis. There is some literature to study the learning rate and its impact on the non-asymptotic analysis. So in particular, even though gamma can take the value between 0.5 and 1, the recommendation is to take gamma as small as possible. So in this work, we take gamma equals 0.501. So I'm going to discuss some of the numerical analysis in terms of how this alpha t will affect the results in the next few slides. So in order to provide a full online algorithm, the variance estimator should also be updated online without solving all historical data, which is actually what we're doing. So here we give the estimator for S and H. You can see that at every step, we only need OS, the observation at the current time, to update ST hat and HT hat, so it's truly online. And we also need one more assumption to get the consistency of the online plugin estimator, which is trivially true when this function are bounded or the second order derivative, they do not involve beta at all. It also holds when the parameter set is a compact set. So having the parameter inference, next we're going to do some value inference. So the value of a given decision rule D, recall it takes this form. So we care about the optimal value, and we also want to update its estimation online since we would not store all the historical data. So we consider to extend the IPW estimator in Zhang et al. To be an online version. So we define the decision consistent indicator, that is when the assigned treatment or action is the same as the optimal action. And the propensity for such a decision consistency, that's a probability of this assigned treatment is the same as the recommended optimal action, given the historical data. So the online inverse probability weighted estimator is then take the following form. As you can see, as long as we store the last stage value estimator, you only need to update with the current data CT and YT. We also note that this pi CT is given, is fixed 1 minus epsilon u over 2. Therefore, we don't need to estimate every time. So next, we can establish the asymptotic normality of the online value estimator. More assumptions are needed, and those assumptions are commonly assumed in the literature to constrain the complexity of the involved functional class. So next, we'll introduce the asymptotic normality of the value estimator, where we also provide a value, the variance of the value estimator with its asymptotic results established. So next I will talk about some numerical studies just to illustrate how the performance of the proposed method depend on the exploration rate. So in this case, see, we're having this gamma fixed at minus 0.501, but we vary the choice of alpha just to represent how large the learning rate. And we also consider a decreasing learning rate, epsilon t, that is, it is always decreasing. You see this t minus t to the power minus 0.3, but it's always above 0.1, so it's going to converge to 0.1. So we use the first 50 samples at burning period, and then starting t equals 50 to do the exploration. So here are some results. In the 3 panels, we present the bias of the data and the bias of value and the performance of the loss, respectively. As you can see that we vary the choice of alpha. So remember that represents the choice of learning rate. So you can see that the different learning rate does not have too much impact on the performance of the value estimator, but in terms of the parameter estimator, the larger the learning rate, C1 alpha equals 1, that's the green line and the green panel, it does have larger variance. If we decrease the choice of learning rate, C1 alpha equals 0.1, it does seem to have a slower convergence. This behavior is similar for the case of the generalized linear model, the logistic regression case. This suggests that we cannot take the learning rate too big because that cannot lead to large variance, and we cannot take that too small because that will lead to slow convergence. So based on our numerical observation, we set alpha equals 0.5 for the following experiment. So the next results are about the parameter estimation and the value estimation with the dots in the right side as the true value. It does seem to show the convergence. And this panel really just shows the asymptotic performance in terms of the inference. So we show the ratio of the average standard error and the Monte Carlo standard deviation, the coverage probability, and the average length. So it does seem to be consistent as t gets larger. And I also want to mention that based on those performance, the diverging, the decreasing exploration rate seems to perform better than the fixed exploration rate when they have the same limit. The same performance shows in the logistic reward model in terms of the estimation and the coverage probability behavior. So here's a summary of the empirical observation, which I already discussed. Just one thing I want to emphasize that according to theorem 2, epsilon infinity, the limiting exploration rate has little effect on the variance of the value estimator if it's close to 0, which is the case in our simulation studies. Next, I want to just quickly show that we did try some other variance estimation methods, and turns out our methods perform the best. So next, I want to just quickly talk about our real data analysis. So we use a Yahoo News recommendation data in the first 10 days of May 2009. We choose 2 most commonly recommended articles, and we denote that as our treatment or action 0 or 1. So the 2 articles are recommended about 400,000 times, and the click rate is 4.1%. So each reader has 5 continuous covariates summing to 1. And we keep the second to the 5th covariate and set the first one as 1 to form our feature vector xt. So we use a reward yt equals 1 for a click on the recommended article and yt equals 0 for no click. So the problem of the news recommendation can then be modeled as finding the recommendation rule that maximizes the value. So this is how we form the offline data to an online decision-making environment. At time t, one entry of the covariate decision rule and reward is loaded from the offline data. We then apply the current estimated decision rule to the covariate x and make a decision a prime. So if a prime is the same as the current a, then we take the entry to update the reward model and set it to the next time point. Otherwise, we discard this entry and go back to step 1. Because this is a the data set is randomly set, so then we select data entry like this will not introduce sampling bias. So the same learning rate from the simulation is used, and we apply with our algorithm for both fixed and decreasing exploration rate. So we've considered epsilon t equals 0.2 for the fixed exploration rate, and epsilon t equals this quantity with limit 0.1 for the decreasing exploration rate. So in either case, we have about 200,000 entries are matched, and the cumulative click rate over the matched entries is about 5.08% and 5.06% respectively. So we do statistical inference as introduced previously for the parameter and the value. So it turns out that in terms of the parameter, beta 04, beta 14, those are the parameters for the first feature for both treatment 0 and treatment 1 are not significant. Other parameters are significant. And this value seems to be significantly above 4.1%, which is the current click rate from current data. In terms of that, this is not covered by the coverage by the 95% confidence interval. So the same observation, similar observation follows when we apply the decreasing exploration rate. So that just ends my talk today. I also wanted to acknowledge that this is a joint work with my student Haoyu Chen and colleague Wenbing Lu, and this work has been accepted by JAXA. You can find the full version in archive paper if you want to know more details. So I will stop here. Maybe we can have time for some quick questions. Here are the references. Thank you.
Yeah, thanks to the Ray for the nice talk. And any questions from the audience?
So Ray, I have a very simple question. Can you hear me?
Sure. Yeah, I can hear you. Yes.
Yeah. So here you do online updates, right?
Yeah.
Every step. So I can also online updates, let's say according to some schedule, right? Let's say in the future, updates just like slower and slower because parameter getting more and more stable, so that I could speed up computation. Would similar theory work? Let's say if I double in the updates, right? The first time, let's say schedule is 1 unit, second time be 2 units, and so on. Would that work or?
So you're saying instead of doing that every time step, I do it.
Yeah.
You're saying like
Once a while, yeah.
Once in a while. I think that's a very good idea, and I think that probably similar in rationale with the literature. Let's see. So I think this is probably called the related, may not be exact same, the forced sampling method. So they just define some pre-specified step, and those steps they allow random exploration. So I think your idea, somehow you're saying as t gets larger, I don't need to do random exploration, or I don't need to change my exploration rate, but I probably can pre-specify that, can pre-schedule the change at a certain step. So I think maybe, I don't think they were discussed, well, to my best memory of the method you mentioned, but I think it's similar in rationale. But I definitely think that's a possible way to do more efficient random exploration.
Okay, thank you.
Thank you.
Any other questions from the audience? If no further questions, so we thanks the Ray for nice talk, and also want to thank all the speakers and Michael and Susan, also Ray for their nice talks, and we learn a lot. And I think and this is the end of the first sections, and actually we have the 10 minutes tea break, and we'll come back at 10:10. Okay. See you then.
Thank you, for the question. See you.
Thank you. Nice talk.
Thank you. Okay, Tony, could you share your screen?
Hi, sure.
Mm.
Can you see my screen?
Yes, I think I need to introduce you. And actually, good morning and good afternoon and good evening, everyone. And it's my great pleasure to introduce my former colleague and Tony Chen, Dr. Tony Chen. Okay. And Tony is a principal research scientist and the director of the reinforced learning group at the DDI Labs, and working on the core problems in ride-sharing market optimization. Prior to GD, he was the research scientist in supply chain and the inventory optimization at Walmart Global E-commerce. Tony received his PhD in operation research from Columbia University. His research interests span optimization, machine learning, with a particular focus in reinforcement learning and its applications in operational optimization, digital marketing, and smart transportation. He has published and served a program committee members in numerous top-tier conferences and journals in machine learning and optimization. And he and his team received informed Daniel H. Wagon Prize for Excellence in Operation Research Practice in 2019, and was selected for the Europe's 2018 Best Demo Awards. And Tony holds more than 10 US patents in intelligence transportation and e-commerce systems. Welcome, Tony. It's your turn.
Thank you, Professor Zhu. Good morning for our audience in China, and good evening for those of you dialing in from the US. I'm Tony Chin. I lead the Decision Intelligence Group of DDI Labs. And I'm very glad to be here to talk about some of our recent works on reinforcement learning for ride-hailing marketplace optimization. And here's our agenda today. So I'll talk about our works on vehicle repositioning, including the development and training of a spatial temporal state value network, and the repositioning algorithm for large fleets that aim to optimize group level metrics. Then I'll go on to introduce our latest research on the new generation method that strategically integrates both order matching and repositioning into a single algorithmic framework, and solves the current bottleneck by combining offline learning and online on-policy updates. At the last part of the talk, I'll talk about the open simulation platform that we recently released to provide a benchmark for ride-hailing algorithms. Online ride-hailing is a form of shared mobility emerging in the last decade and gained incredible prevalence around the world. As it becomes apparent that the traditional modes of transportation are unable to meet the growing travel demand, people are increasingly relying on crowdsourced mobility supply through ride-hailing. And at a lot of places, this is an integral part of our life. And some auto industry experts have even predicted that ownership of private cars might become optional in view of ride-hailing. But on the other hand, operational efficiency of ride-hailing marketplaces is a long-standing challenge, which includes the waiting time for the passengers, the idle rate of the vehicles, and the drivers chasing transient hotspots sometimes. So the optimization of core decision problems in the ride-hailing marketplace has a profound impact to all of us. So here, trip requests and vacant vehicles are matched and transactions completed within the ride-hailing marketplace. And this is a two-sided marketplace where both the drivers and passengers are important key players. To the drivers, income and their idle time or in-service ratio are something that they obviously pay much attention to. And to the passengers, their ridership experience mostly reflected in the pickup waiting time, and order response rate and fulfillment rate. And the platform therefore cares about all these metrics and tries to optimize them through three major levers: order matching, vehicle repositioning, and pricing and incentives. In my talk today, I'll focus on order matching and vehicle repositioning in particular. The process of order matching starts from the potential passenger keying the origin and destination into the app. And the platform offers a quote for each product. So for example, here, if I select Express in this case and submit my order, and this is where the matching process begins. The system then searches for a vacant vehicle nearby to match my order. And upon a successful search, my order is then assigned to a driver, and I know how far the driver is from my current location. Now, if the search takes too long due to low supply, for example, I may drop my request. If it's going to take the driver a long time to pick me up, I could also cancel my order. So in other words, the demand is impatient. And the repositioning of a vehicle may happen after an order is completed and there's no immediate new order coming in. And the system will then send a reposition recommendation to the driver when certain conditions are met. The reposition basically tells the driver where has a better earning prospect than the current location and guides the driver through GPS navigation. And these are some illustrated screenshots on the screen of a driver requisition system program. So why are order matching and vehicle repositioning important from the system's perspective? I'll present several motivating examples here. On the left-hand side, we've got 2 vacant vehicles and 1 open request. If we assign a request to the vehicle in the green circle area, and another request appears in the next few minutes in the red circle area, then both vehicles will be matched. The example on the right-hand side illustrates that the demand condition at the order destination has direct impact to the earning prospect of the driver who completes that request. And in both cases, if the matched vehicle is too far away from the passenger, as we saw in the previous slide, the passenger may cancel the order. So the current matching decisions would influence the future system state, so having impact to the subsequent matching results. So in the matching optimization, we need to consider the long-term value, not just short-term returns. And here's an example of repositioning. We've still got 2 vacant vehicles here, and currently there's no trip request. And the predicted demand in the red circle area is higher, and that in the green circle area is lower. But there are already some vacant vehicles in the red circle area. And if we reposition purely by demand prediction, then both vehicles will go to the red area. And consequently, 1 vehicle will be idle once it reaches there. And if we additionally consider the supply distribution, then the vehicles may be dispatched to the different locations, which is an optimal solution over the long term. Our core ideas to approach the reposition problem are quite intuitive, actually. First, we use neural networks and state values to quantitatively represent the spatial-temporal synergy of supply and demand, which directly influence the driver's income. And we consider the long-term values of reposition decisions through reinforcement learning. And we already have a number of works on developing such a state value network to successfully solve the order matching problem. And now, finally, at the decision time, we use planning to reposition vehicles to locations with optimal expected cumulative income. Our approach to modeling the reposition problem is from the driver's perspective. We model it as a semi-MDP problem where we discretize the spatial space by the hexagon grid system to construct a spatial temporal state. The state can additionally include neighborhood supply-demand contextual features. The action, or rather the option here of the agent is to stay within the current cell or relocate to a new place in the neighboring cell. And in our model, the order matching policy is fixed and exogenous. So there's no learning about it, but rather it's represented by a single degenerate option. The reward for a repositioned action is the travel cost and is negative. Whereas that for an order matching action is the trip fee. And we discount the reward appropriately by the trip duration. And let's first recap the several technical highlights of our previous work on CVNet. That's our spatial temporal state value network for ride-hailing. For state representation, CVNet leverages a hierarchical hexagon grid system to learn the sparse quantization through grids of different granularity. We use a cerebral embedding to construct a learnable high-dimensional state representation. Each location is then represented by a sum of embeddings at different scales. And to stabilize the training process of CVNet, we adopted regularization at each network update by adding a penalty term to the loss with the Lipschitz constant of the network. The update scheme of CVNet is similar to TD learning and DQN, where each order assignment or idle cruising is a state transition experience. And here we pull the experience from all drivers in the system to train the single value function, which is then shared by all the drivers at decision time. And in this way, we can effectively handle the issue of time-varying size of the agent group due to online-offline behavior of the drivers. The modeling of the value network is from the single driver's perspective to interact with the environment. And for cases of large fleets, there are a few new challenges. First is coordination among the agents or drivers. In the case of small fleet, every vehicle can be thought as operating independently within the environment. And as the fleet grows, the repositioning of one vehicle may affect the other ones. And in particular, we need to avoid the so-called overreaction problem. And back to the motivating example I described earlier on, if we reposition purely by predicted demand, then both vehicles will be sent to the same area. And one of them will be left idle due to oversupply later on. And the passenger in the green area will have to wait. And the other challenge is computational complexity. If the number of requisition requests within a given window is large, a complex decision time planning algorithm will have difficulty to meet the latency requirement in production. So we decided to use SASA to learn the queue function through offline policy evaluation. And in the design of the SASA value network, we have added contextual features to the state, including the supply-demand features of the current and neighboring cells. This is to allow the value network to be aware and adaptable to the dynamic supply-demand context. And we also leverage an attention module to learn the association among the neighboring cells and generate the supply-demand context vector. And similar to CVNet, the deep SASA network has hierarchical coarse coding and the cerebral embedding for spatial features. And we still use Lipschitz regularization for training stability. The SASA network has multiple output heads and each corresponding to a reposition action. And in executing the reposition actions, we use a stochastic policy. And specifically, we add a softmax layer to the end of the SASA network to obtain the Boltzmann distribution of the action values. And the action to execute is determined by sampling this distribution. Our empirical experience shows that for a large fleet, stochastic policy significantly outperformed the greedy policy with respect to the action values. The reason is simply that the stochastic policy distributes the vehicles within the batch to different destinations by their action values in expectation. And this property naturally handles the overreaction issue mentioned earlier. And since the action value now governs how a batch of vehicles are distributed, we further use the supply-demand gaps in the destination cells to regulate the Q values. And we set a threshold for the supply-demand gap in the same way as a hinge loss, since the short-term supply-demand are highly stochastic. And as we'll see in the next generation method, this kind of treatment might not be necessary because of the fast adaptation of the value network. To evaluate our repositioning algorithm in the real-world environment, we actually recruit about 1,200 ride-hailing drivers from 3 cities in China to participate in our experiment program over 2 phases. Those drivers receive reposition recommendations, and we refer them as the algo group. And the control group is sampled from the regular driver pool. And here are the main results. We compare the performance of the 2 groups in 2 metrics, the income rate and the utilization. They are both computed at the group level. And we can see that over the 3 cities, the algo group outperformed the control group by about 3 to 7% in both metrics. But of course, there are variations among the cities. And the major factors here are the overall supply-demand ratio and the skewness in the demand distribution. And so just now we looked at the group level results. And let's also take a look at the distributions of the individual level income rates. Here we divide the IPH, the income per hour, basically the income ratio, the income rate, into equal size buckets by value. And then we look at the histograms of the 2 groups. The y-axis is the percentage of the drivers within that group whose IPH values fall into the given bucket. And we observe that the IPH distribution of the algo group lean towards the right, indicating higher overall income rates. And the skewness is also consistent with the group level results that I showed in the previous page. Now, so far, the methods deployed in industrial production environment in the ride-hailing domain are basically all based on offline learning. And the major bottleneck is that frequent updates to the model and policy through deployment is not practically feasible. Although offline reinforcement learning captures the primary patterns in the daily spatial temporal values, it's unable to adapt to the long-term values to real-time supply changes and the consequences. And we believe that the next performance breakthrough for reinforcement learning on the ride-hailing province basically lies on the fast adaptability of the value function and the joint optimization of matching and reposition. And we call this next generation method V1D3 for unified value-based dynamic learning framework for order dispatching and driver repositioning. And our paper on this work has been accepted by KDD this year and is available on arXiv. And there are 2 highlights in this new method. First, we present a novel way of joint optimization for matching and reposition. And its mechanism is highly practical and easy for deployment. The other highlight is the integration of offline learning and online on-policy updates, making the value function adaptive to the dynamic environment. And matching and repositioning are highly associated problems in that both operations would change the spatial temporal distribution of the vehicles. So for system level optimality, these 2 policies should be optimized jointly, right? And the question is, how should the joint optimization be done in practice? The most direct approach is to explicitly formulate the matching and reposition problems as one single optimization problem. However, the invocation time and frequency of these 2 policies are quite different. And they typically belong to different modules in the real systems. And on the other hand, we can use spatial temporal value function to guide both policies. So we have adopted an implicit method by sharing the value function between matching and reposition. And this also makes it easier to deploy this framework because it fits the current system architecture better. And the next question is, how can we make the value function adapt to the dynamic supply-demand context in a fast and robust manner? Offline learning algorithms are trained on multiple days of data, so it's easy to capture the day-on-day supply patterns, whereas pure online learning can effectively capture the intraday non-stationarity, but it sees only the data up to the current time of the day. So we combine the two value functions through Ensemble to get the best of the two worlds. And on the right-hand side, we show the mechanism of V1D3. The value function that governs the decisions is updated by real-time matching and reposition results and supports the output of the two policies simultaneously. And let's look at the value function updates more closely. The on-policy updates can be done in each order matching window through the TD updates using trip and idle cruising transitions for matched and unmatched drivers. And these updates have very low computational complexity and can easily satisfy the latency requirements in production systems. And for offline learning, we adopt CBNet that I described earlier to perform policy evaluation on large historical data. How do we implement Ensemble? Do we have to do it frequently? In fact, high-frequency Ensemble not only increases the computation, but leads to overly conservative online updates. So we propose a periodical Ensemble method. First, we leverage the historical data and change point detection algorithm to identify the times when the order distribution starts to shift during a day. And they basically correspond to the transition periods between off-peak and peak hours. So we don't really need a lot of them. Then we perform weighted combination of the offline and online value function at these points. And last year, we hosted the KDD Cup reinforcement learning track competition. The topic of that competition is exactly on ride-hailing matching and repositioning. The two tasks are evaluated simultaneously within the same simulation environment and are scored based on the cumulative rewards, which are the total income for matching and average gyro income rate for reposition. And our method that combines offline learning and online updates outperform both champion solutions on their respective tests. The simulation benchmarking on 3 cities over both weekdays and weekends showed that V1D3 achieved a significantly higher matching score than the champion solution for matching tasks. And comparing to previous SOTA, the CVNet algorithm, V1D3 also outperformed by a wide margin of about 5%. And on the reposition test, the performance of V1D3 equally outstanding. And here, the number of vehicles managed by the reposition algorithm is a parameter, and we have tested various numbers from 100 up to 2,000 to look at the performance trend of the algorithms. And we can see that V1D3 yields the least performance drop among the baselines, including the champion solution. And the standard deviation over different seeds is also small. So this shows that V1D3 handles the coordination pretty well in the case of large fleets. Its overall income rate is also significantly higher than the champion solution and expert driver policies. The main advantage of V1D3 is that it only needs to maintain one single value function to obtain the optimal policies for both matching and reposition. When the system is running, the matching results automatically update the values required by reposition policy. So V1D3 is also resilient to suboptimal reposition policies by immediately updating the value function with subsequent matching results. So let's look at two case studies. The top and bottom rows show the situation before and after a major event in the city. Right before the event, the venue, which is center of the center cell in the diagram, sees a surge in idle vehicles due to a lot of drop-offs at the same time, and that leads to a large decrease in the value in that area. The magnitude of the drop decreases as the distance from the epicenter increases naturally. As time passes by, the matching and reposition policies will bring the value distribution back to normal. And we've got a similar but reverse observation for a post-event scenario. So such the ability of the value function to respond quickly to non-recurring events directly translates into the adaptability of the policies to real-time supply-demand changes, and thus solving a major bottleneck that motivates this work. And as we know, decision optimization goes hand in hand with the evaluation environment. And this is especially true for research in the ride-hailing domain. And researchers often have to develop the simulators for evaluation by themselves. So as a first step to address that pain point, we have released an open ride-hailing simulation platform for standardized benchmarking. This is an industrial level simulation environment based on real world scenarios with the following highlights. First, it supports joint evaluation, matching, and reposition policies in a single environment. And we provide multiple environments for validation and testing purposes to prevent the algorithm from overfitting the environment. And there's a leaderboard for each environment and task so that we know where our algorithms stand compared to our peers. Last but not least, this platform offers Python API. So development is really easy and the algorithm can basically plug and play. And to get started, all you need is an account with our Gaia program. And the QR code at the right-hand corner will basically get you there. And these are the papers that of my team referencing my talk today. The core contributors of these works, Xiaochen Tang, Fan Zhang, Shaiji Li, and our current and former colleagues and intern students have all put in a lot of effort. And we have also recently released a survey on reinforcement learning for ride sharing, covering all the major topics like matching, repositioning, pricing, and ride pooling. And it's going to appear at the IEEE ITSC conference, and it's also available on archive. So I'll end my talk with a small ad. We are hiring full-time researchers and engineers in both our Silicon Valley and Beijing offices. And feel free to reach out to me using my contact information here if you are interested. And we are also organizing the reinforcement learning for intelligent transportation systems workshop at the IJICAI conference in August. So hope to see many of you there. And if you missed the QR code for our open simulation platform just now, here it is on the top right-hand corner. And thank you.
Tony, any questions from the audience?
Hello, Tony. I have a question. So I wonder if, what's your opinion? The question is that, do you think the reinforcement learning is the answer to implement artificial general intelligence? I saw some papers talking about that, so I want to know your opinion from your experience. Thank you.
Yeah, artificial general intelligence. Yeah, that's a. I saw that statement. I think it's from David Silver's slides. Well, as a researcher, also in areas related to reinforcement learning, I think this is definitely a very promising way towards that ultimate goal. Because eventually, if we want to eventually replace human beings, we got to allow the algorithm to, with the ability make decisions, and so that is basically optimization in a dynamic way. And currently, I think reinforcement learning is definitely a very promising approach to that problem. Of course, there are other very good dynamic optimization algorithms, but I think reinforcement learning, for example, you can integrate RL very effectively with and leverages all the advances in deep learning, and that basically presents a very large advantage for reinforcement learning. So yeah, if you ask me, yes.
Okay, thank you.
Any more questions from audience? Okay, if you have no more questions, I think Tony, can you stop sharing your screen?
Thank you.
You know. You know. Yeah. What's the name?你他们没进来啊？
当然了，我不能传六十题，然后也不能 start video，也不能 share，不知道为啥。
You cannot share, you cannot start with. What happened? 那个谁给黄老师这个？应该。
Just one. Yeah. It asks for permission or something like that. Just okay.
Yeah, I think I can start first. I think it's my great pleasure to introduce Professor Linong Kong from University of Alberta. He's currently he's an associate professor in the Department of Mathematics and Statistics, and he's holding the Statistical Learning Research Chair in Canada, and he has published over 50 plus papers in top tier journals, including Annals of Statistics, JASA and JSSB, and also the top tier conferences, including ICML, ICDM, AAAI, IGK. And Dr. Kong is the associate editor for the JASA and also International Journal of the Imaging Systems and Technology and the Canadian Journal of the Statistics. And his research interest includes statistical learning, high-dimensional data analysis, and the neural image, and the robustness statistics, and the quantum regression. Now it's your turn, you know. Can you share your screen?
I still can share my screen.
Yeah.
Hello, Professor Paul.
Yeah.
Could you
I
share
think
your screen?
it's probably
嗯，
I'm
洪老师
trying
您
that.
好，您能那个共享屏幕吗？
What's the problem?
您好，您能共享屏幕吗？ 您先看一下最下面有一个共享屏幕，有静音、停止视频、共享屏幕，您可以点进共享屏幕。
本教授到底咋回事啊？
刚才那个网站，我微信问他了。
哦，对，朱老师找，朱老师，
这个他口耳是现在这个没办法限你，他能用我们的讲吗？
什么用我们的什么讲？
就是用我们的 Zoom number 去讲吗？
哦，可以的。
那你把 Zoom 给。
那我们可能都要换一下那个，稍微就直播要暂停一下，然后换一下 room，然后让
你现在看他 Zoom 行不行？回来我来看看我们用 Zoom 行不行
Until he was able to speak, if he was using Wu, I look like I can share, so you can just advance his slides, then he can talk.
Linong, could you send me your slides? I can play the slides for you. You can speak if you can.
I don't think he's online now. He was online, but currently he doesn't look like online. But if he could do what he did before, you can just advance slides for him.
Yeah.
Yeah, I think Lin Long is still in the attendee list. Yeah.
讲吗？
周老师，你收到了吗？
可以啊。
哎，你好，
那你
孔老师，你看
那你
这回
帮我，
可不可以去啊？
我现在还是不能下。
不然的话，您可以把 PPT 发过来，然后在这边我们给您那个 share PPT，然后您只讲，
啊，我把 PPT 发给周老师。
发给周帆也可以。
发给我。
哦，我转给你们吧。
你有周帆老师的微信吗？请你。线上线下就是很多不可控的这个大家见谅。可以了，是吗？我们这边已经可以显示 PPT 了，然后我们把它放到那个会议室共享。
哦，好像可以了，我们现在能看到你那个 share 的。
哦，
可是我 share 了吧？还是你去 share 的？
对，周老师，
应该是朱老师 share 的，那个 user 是红图。
好，孔老师，那应该是可以开始了，因为朱老师share 了您的 PPT。
哎，别慌，别慌，我都看不见我自己。嗯，怎么 full screen 呢？我怎么看不见我自己？
张明，你这边收到没？要不然我们这边共享，
你们
这边
共享吗？
也收到了，你们收到了。
你们共享。
好的。
嗯。
可以。
Okay, thank you. First, I apologize for all these things. I used to use this valve, and I was able to share screen, and I should check this this before the meeting. And thanks, Fan, for helping me with this. So today I'm going to talk about exploring the robustness of distributional reinforcement learning against noisy state observations. So this is a joint work with my student Ke Sun and my student Yi Liu, and visiting student in Nanzhao, and my collaborator Rui Bo and Heng Shuaiyao. I will first give a brief introduction about reinforced learning and distributional reinforced learning. And then I will talk about this state noisy Markov decision process and the analysis in expectation-based reinforced learning, and also how we do it in distributional reinforced learning. And then we look at the situation beyond state noisy MDP at different noisy setups. We look at this TD convergence, and also we look at sensitivity analysis. And by the end, there's some experiments including some Atari games, and then there's conclusion. So first, this reinforced learning, this is a typical Markov decision process, and the agent interact with the environment, and then we can model this process as a MDP as a 5-tuple. We have S as state, A as action, then we have this transition probability P from a certain state, you're taking action and transfer to the other state. And we also have this reward function. And this gamma is a discount factor. So in traditional reinforcement learning, and we would have this value function. This value function represents a cumulative reverse following a policy pi. And here this R is reward. It's a scalar reward obtained in the step T plus K plus 1. And this we use that pi as a to denote the state action value distribution. And In particular, in this expectation-based RL, we have this value function. This value function is defined as this V pi S. Why we call it expectation-based reinforced learning, and sometimes some people call it mean-based, because we take the expectation of this value distribution and given the current state. Now, for this expected based reinforced learning, we have this Bellman operator T, and this T transfer this Z pi SA into the following format. Now, why we only care about the expression? What about we look at the whole distribution? So in this case, the value, instead of have a value function, we have a value distribution. So distributional reinforced learning focus on the full distribution of this value of this random variable. And in this case, we still have this transition operator and can define in this following format. Here we use S prime, capital S prime, capital A prime to emphasize the random nature of state and X. And here D, that means it converts in distribution. Just like the expectation-based reinforced learning, for distributional reinforced learning, we also have this Bellman operator. And here, this Bellman operator, instead of impose on this value function, we impose it on value distribution. And this T pi, like expected based reinforced learning, this operator, this Bellman operator or distributional Bellman operator is still a contraction for policy evaluation under the maximal form, of course, in terms of this versus the matrix, because it's different from the expectation-based reinforced learning. Now we have to define specific metrics in order to have this Bellman operator to be a contraction. Now, next we will look at this state noise or Markov decision process. Why we want to look at this situation? The motivation is we want to study the robustness of this distributional reinforced learning. And for the robust performance of the algorithm, it's very important. We want to look at this systematic or stochastic measurement error. We want to look at the impact of external and adversary disturbance. And now to explore the more benefit about the distributional reinforced learning, for example, the current the existing benefit, we can improve the sample efficiency, we can have better performance. But what else benefit this distributional reinforced learning may have? And here is our motivation. We look at the robustness of this distributional reinforced learning on some different noise setup. For this robustness, we can have sort of, the training robustness or this testing robustness. In our work, we focus on the training robustness of distributional reinforced learning against noisy states observations. Our contribution mainly focusing on the following three. First, we establish a theoretical convergence analysis for both expectation-based and also a distributional Bellman operator on a new defined state noise MDP. Secondly, we investigate this PD convergence under more complex noise scenario, and also provide some sensitivity analysis through using influence function. We also demonstrate that the distributional reinforced learning approach actually enjoy better robustness under different scenarios than the expectation-based reinforced learning through some experiments. Now let's look at our setup. Now traditionally we have agent at a different state, and the agent take action, and then we get a reward. We interact with environment, then we get a new state. And here we introduce a sort of state noisy MDP, and instead of these 5 tuple, and we now have 6 tuple. We have this noise mechanism, and these mechanisms map the state S to VS using either random or adversary noise with Markov and stationary probability and VS given S. Here we only manipulate this state observation, but we don't change the underlying environment transition dynamic based on S. The underlying environment still keep the same, but the difference is the state we observed may have some noise. So for this SNMDP, for this expectation-based reinforced learning, and we can define a new value function. This new value function essentially get considered these noise generation mechanisms, and we show under this SNMDP, their Bellman operator is still a contraction, and then we can look at the convergence of this Bellman equation. In particular, we showed this these 2 properties. One is under this SNMDP, this Bellman operator is a contraction operator and convert to this V pi prime. The second one is this operator TA pi is a contraction with convergence satisfy the following thing. Yeah. Now this is for this expected. This is for the expected expectation-based reinforced learning. What about for distributional reinforced learning? We also showed that for distributional reinforced learning, or distributional Bellman operator is also a contraction under this setup, under this state noisy MDP situation. And now this property would guarantee, if we have this state noisy situation in either traditional expected reinforced learning or distributional reinforced learning, the classical algorithm and all these things still works. And but what about we have a more complex noisy situation, whether this expected reinforced learning or distributional reinforced learning still works? Now we look at 3 different situations. In TD learning framework, the adversary might perform attacks at certain intervals, yielding unbalanced state noise pairs or measurement error exists unevenly between state observations. So basically, there could be 3 situations. One is we have a noisy current state and benign next state, or the benign current state, and we have a noisy next state. And the third situation would be noise current state and noise next state, which is the state noise MDP we already discussed. Now, to analyze this, we conduct our analysis in using linear approximation setting under TD learning. Okay, for TD learning, let's just recall what's TD learning. This TD convergence. For TD update, at step T, we would have the this update steps. And for the expected form, it is this one. This is all the traditional formulas and all the known formulas in this Rich Sutton's textbook. And we know that the matrix A determines this convergence in the linear TD setting. But if we add a noisy and state noise eta on either xt or xt plus 1 current or next state, whether the convergence condition will change or not. Now, we actually have the following three situations: the condition for TD convergence under noise state observation. The case 1, we have both A and these are positive definite. The case 2, we have A and this minus X transpose the DPE are positive definite. Case 3, A is positive definite. There are actually some trade-offs in case 1 and case 2. And unlike this, we have through sensitivity analysis using this influence function. So we conduct an outlier analysis in the TD learning via the influence function. The influence function is that with this contaminated distribution F epsilon, and then we have this start X, so we have an outlier X, and using this contaminated distribution for a estimate, for example, regression estimate from this data, we can define the influence function of the theta at F as this format. Okay, essentially or mathematically, this influence function is this Delta-X derivative of theta at F in the direction of dot X in the outlier direction. So for this sensitivity analysis, we see this influence function of this psi actually can be written in this format. This is what does that mean? We have a sort of a corollary, and we can conclude the sensitivity of the current state, which is case 1, and the next state, which is case 2. The state features against perturbation is normally divergent. So this is the sort of the degree of sensitivity is heavily determined by the task, which we will show later on in our experiments. Now, for this is actually for expected expectation-based reinforced learning. For the distributional reinforced learning, unfortunately, it's more complicated. We cannot get anything similar to 9. But we actually did some simulation. The results show that the distributional reinforced learning is more likely to converge, which means it's less vulnerable to noisy. It's more robust than expectation-based reinforced learning. Now let's look at some experiments. And the algorithm we are looking at is DQN and QRDQN. And the environment we look at this catapult and mountain car and breakout and Q-bad. Breakout and Q-bad is two games from Altera. And the noisy situation, we look at a noisy state observation, random noise, and adversarial noise. Now let's look at this handball game. And this solid line means without any noise. As you can see here, without noise, and the QR DQN is better than the DQN. Okay, and in this situation, if we have some adversary noise at current state, this adversary noise at next state, adversary noise at the current and next state, we can see this QR DQN is more robust than DQN, and the same perturbation strength, and which you can tell from this red one always better than this the other colors. And the next observation, which you see in the middle one, are less vulnerable than the current one, yeah. Now, if we look at these mountain car games, if you look at these three situations, here we use random noise, and we see we can still see this QRDQA is more robust, or at least comparable to this DQN. And the next state observation are less vulnerable than the current state, and which is all you can say is more robust. Now let's look at two Altera game. We look at this breakout. The breakout, as you can see here, we can also see this QRDQN is more robust than a DQN under perturbation strength, and we get similar conclusion. The next state observation are more vulnerable. More vulnerable than the current state. However, the QRDQN is still more robust than DQN, which means the distributional reinforcement learning is more robust than expectation-based reinforcement learning. And here we actually have a different situation. The next state observation is more are more vulnerable or less robust than the current state, which is different from previous one. But nevertheless, the distributional reinforcement learning is more robust than expectation-based reinforcement learning. And we look at another Altera game, which is Q-bad, as you can see here. We look at this adversary noise situation, and this distributional QRDQN is still more robust than DQN. Then the next state observation are more vulnerable or less robust than the current state one. And yeah. So the conclusion we have here is both expectation-based and distributional Bellman operator contraction converge once in state noise MDP, but the convergence condition is harder for more complex noise setup. For example, if current state or next state, and experimentally, distributional reinforcement learning algorithm is more robust and less vulnerable, more likely to converge than the expectation-based RL. And of course, our setup is in the training situation. And the sensitivity trade-off between current and next state exists, and its order depends on the game. Sometimes current state is more vulnerable. Sometimes next state is more vulnerable. I think that's all for my talk. Thank you.
Any questions from the audience?
I think I have two questions. So the first one is, I think according to your experiments, it seems like it's like a tool to test the performance of different reinforcement learning algorithms. So I was wondering if it can help like increase the performance of the existing RL algorithms. I mean the state noise tree.
It may. The reason we choose is DQN and QRDQN. There are many, like you said, there are many different algorithms. The DQN and the QRDQN is it's like the two typical algorithm in expectation-based RL and distributional RL. And there are, of course, exist some other algorithms.
Yeah, so do you think this kind of idea can help like increase the performance of like maybe DQN or QRDQN if you add a noise into the training?
That's a good question. That's actually what we want to do next. Yeah, we don't know.
I think my second question is that I think for some of the games, DQN performs more robust, and for the others, QRDQN performs better. So I don't. Can you explain a little bit about the reason behind that, or maybe it's because of the environment setting or some other stuff?
I think it purely depends on the game, and I think for my experience is for distribution RL, it performs better when the environment is more complex and need better representation of the environment. Yeah.
Hi, Linglong. So I do have a very naive questions to ask about because I know very little about reinforcement learning, but I'm interested in you mentioned about you didn't provide any theoretical guarantee for distribution like distribution reinforcement learning. So is there any special reason about or challenging part you find that is different than without consider about the distributional like reinforcement learning about theoretical property? So what would be the challenging part, or you just you guys just didn't do it yet? So yeah, that's what I'm very curious.
We tried, but we couldn't get a reasonable result. Yeah, I think you know distributional reinforcement learning, we treat the reward as a distribution. So this add another layer of the variation when we trying to derive the formula, trying to derive the influence function of this noisy or less.
Okay, so yeah, because I think we have read this paper about how to quantify those difference between those two measures. That basically we are comparing like two functions, and yeah, I was thinking about what we the
yeah, when we do this when we do this paper, we didn't know that technique yet.
Oh yeah, okay, yeah, yeah, probably that might help a little bit for the proof. Yeah, thanks a lot.
Thank you.
Any more questions?
Well,
Yeah,
dear Professor Kong, I'm a graduate student from Xi'an Jiaotong University. May I ask a minor question? Because, excuse me?
Yeah, I can hear you.
Yeah, I'm a little bit confused about the Formula 9, about the influence function, your sensitive analysis. I want to ask a question. On a statistic perspective, from the influence function, we can see that it is proportional to the xt, the current state. So how could we understand the robustness from the statistic perspective? I'm a little bit confused about it.
Actually, I'm not quite understanding your question.
Oh, well,
so the basic idea is we want to quantify how our reward get affected by the outlier pair, and let's say xt plus 1. Then
yes.
we derive the influence function of if we have outlier pair xt plus 1, and then we try to analyze how this outlier pair would affect our reward.
Yeah, maybe I will learn it later because I don't work on reinforcement learning. I just see it from the statistic perspective, and I say it is proportional to the current state, and I don't understand the robustness. So
well, so basically this influence function, if you go back to the original definition of the influence function, and here we also look at the linear functional approximation. Maybe this influence function is proportional to this current state, and also related to this reward. It might be what we expected.
okay. Okay, thank you, Professor.
Thank you for the question.
Okay, I think I will just stop here. And I think this is the final talk for this section. I think we are going to have a discussion sections about the future of the reinforced learning. Tony, it's your turn. Yeah, you can speak Chinese if you want to.
Yeah. So what's the consensus?
It depends. You can speak English or Chinese or whatever you like to. I don't care. The most important thing is we needed to talk openly and discuss the futures of reinforced learning. Yeah.
Okay. So for for the the continuity of the conference. So maybe let's just continue in English. It's fine. Yeah. So welcome to today's panel. I'm Tony Chin, and I'm your moderator today. So let me first introduce our panelists today. Yeah, I see Zhao Ran Wang, Professor Zhao Ran Wang from Northwestern University, and we have Professor Lin Long Kong from University of Alberta, our last speaker, and we have Professor Fan Zhou from Shanghai University of Finance and Economics, and of course we have Professor Hongtou Zhu from University of North Carolina, Chapel Hill. I have everybody here, right?
Yes.
Yeah. Okay.
Yes.
Cool. Yeah. So as Hongdu has mentioned, our topic today, or the overarching topic today for the panel, is the future of RL. So we are going to, discuss a little bit about your perspective about future development in RL, and also since I'm from the industry, naturally the questions that I prepared would concern more on the application of RL and the issues associated with that. So as a starting question, so let me poll the panel. What do you think would be the new promising real-world application of reinforcement learning in the next few years, and why? So I'll, for fairness, I would just go by alphabetical order. So how about Linglong, you first?
No, but I think distributional reinforcement learning will definitely be one of the future for reinforcement learning. And even though right now we are still struggling to see, why it works and how it works, but at a lot of situations, it just works better than the traditional expectation-based reinforced learning. And yeah, that's at least I feel one of the direction for reinforced learning. But of course, from this application perspective, I think the work you did for this, this car dispatch here is the real world application. And I think for reinforcement learning, we need to find more real world application. And this AlphaGo is a good start, but the real world application would be able to more strongly motivate the research of reinforcement learning. Yeah.
Cool. And how about Zhao Ran?
I think from an application perspective, I think anything that can be simulated, would be a very natural test bed for reinforcement learning. For example, like you have already achieved a lot of success in terms of like ride sharing. And because I'm working in like OR department, so within our department, there are a lot of people trying to apply reinforcement learning to inventory control, and also, for example, like dynamic pricing and also like supply chain management in general. Well, there are a lot of simulators for those applications as well. And some of them are actually very accurate, except that, there are like a lot of components that remains stochastic and needs to be calibrated with reality. But once, I think, given all those simulators, as long as it's accurate, then reinforcement learning can be applied. And to me, I think there's at least another a very broad class of problems that involves like multiple agents. For example, for the matching market, like Professor Zhu's work, I think he also has a presentation video posted on Bilibili, which I enjoyed very much. And also, there are a lot of related settings that involves like gaming between different agents. For example, like in the trading industry, there are different players, and they compete on the order book. And those are kind of settings I think would be a great test bed for multi-agent reinforcement learning. That's kind of my personal perspective, though.
Cool. Yeah, you mentioned simulation. We'll talk about simulation later as well. And Fan.
Okay. So before I start, I think we have Dr. Bing Liu from Alibaba. I think he can also share with us some views about the application of IO in industry.
Sure.
So I think IO has a bright future. I believe that, but I think before it can be applied to more fields, I think there are some problems we need to solve first. I think the first problem is that if we apply to some real world problems, we need to have some domain knowledge. We need to know how to define the reward. I think that's very important. And also, I think as Jordan mentioned, I think sometimes we need to like build a very good simulator to do the training. I know that in DD we have very good simulator for dispatching and repositioning, but I think in many like traditional industries, maybe they don't have this kind of simulator, and or say they even don't fully understand their data or they don't have data. So at least we should have some efficient sample. I mean, if we want to do like some offline learning, but if we don't have that kind of sample data, or we don't have any good simulator, it's very difficult for us to apply reinforcement learning. I think these two are very important problems we need to solve first before we can apply RL into more broad categories. That's my opinion.
Okay. Okay. Yeah. How about let's hear from Dr. Bing Liu.
Thank you for mentioning me. Actually, honestly speaking, I didn't research into RL very deeply, but from my experience, I think from the first principle, I think RL is collections of different different technologies like decision making, optimization, and also I think its performance highly depends on data. I think its success depends on a good data collection techniques. What's I think the most interesting thing is that what's the limitation of so I also want to know this answer from your discussions. Thank you. I think I don't know what's the relationship between RL and causal inference, like to the first one. I don't know why the industry adopt RL actually, but I didn't know many successful stories of do this works in industry.
You mean the difference between RL and causal inference?
Yeah, the causal inference. I think RL in theory, I think is there is an intrinsic relationship between causal modeling and RL. But RL is pay more attention to data, I think, or big data. It's a data-driven modeling strategy, I think. But causal inference maybe is more theoretical, theory-driven. Yeah, it's my own opinion.
I guess that's also a good question for Professor Zhu. Hongtu, you want to share some thoughts on that? Can you hear me?
Me?
Hong Tu.
Sorry, I didn't turn my
Oh.
video. And okay, I think the I have been thinking the 4 different things because given my career in academia and also my experience in academia and all the industry. Because the early days I studied a lot of the machine learning stuff, or statistics. Then these days we see a lot of people doing deep learning. I'm not it's not against. I know the deep learning is a very powerful tools for solving all kinds of these kinds of like computer vision or these kind of problems. And also when I work at the Didi and I basically work with Tony and also work with the fund regarding to using the reinforcement learning to solve the industrial problems. And but these days I also think of try to use the causal inference to solve the related problems, but from the kinds of evaluation perspective, let's say. And my personally feel this kinds of the path my personally experienced is really gained through the applications and also the depth of applications we're working on. Okay. And you'll see that basically I first thing I'm on comments on the deep learning a little bit. I think deep learning is a very powerful tools when the data is not in the kinds of common spaces. There's a good nonlinear transformation to map the data in the common spaces so that you can do the nonlinear mapping in the transformed space. It's a great tool for CV and also not the NLP and speech recognition. Okay, because that type of problems is deep learning is so powerful for that. Okay. But I personally didn't spend a lot of time on deep learning itself. When I work at the Didi, basically, the more I started to work with Tony by using the reinforcement learning, okay? Because when I using reinforcement learning, usually we have a very concrete problems, and but that problems you can roughly easily to define what is the reward functions, and also you can put all the into the reinforcement framework. But the problem is still is a more, to me, is at the levels is similar to many applications we're working on. Is relative small problems. Okay, I'm not saying these problems is not big enough. I'm saying that most of the problem when we started to work, I used the reinforcement learning. We usually choosing a concrete problem to solve, like reposition and also pricing. Even for pricing, we have a different kinds of problems that we try to solve. But this kind of problems, to me, is if you're looking at a specific applications from the global perspective, okay, you will see that this is all these kinds of small tools we use to solve a big problem. Okay, that's pretty be useful. Okay, but if you're looking at the whole systems like Didi as a company, okay, if you're working at a city or even the whole country or the whole world, you think about the platforms like ride-sharing platforms, and from that perspective, and then the single system like reinforcement learning won't work very well in that aspect because the problems, there's too many subsystems, and that each of systems you could solve by kinds of the specific reward function for that system. But you know that if you work in the whole market, and the ride sharing kinds of the platform is a part of the whole cities. And then this is part of the small portion of the whole transportation systems. And then you think about it, if you from that big perspective, And that's the total different story, okay? And that's the reason, and we go back to think about another set of questions, is if we only optimize one aspect of the problems, and using reinforcement learning. But if you think about the kinds of from the global perspective, what is the right tool for that? And there's no, I don't think there's a single method or single tools can solve all these big applications. And the causal inference, I personally regarding the reinforcement learning is a part of the causal inference. In the sense of, I think because you're trying to find the policies, and the policy influence the reward or influence the outcomes. Okay, and if that policy doesn't, it's not a causal effect. In general, I don't think that's the kinds of the relationship that are valid in certain sense. That's my personal opinion. Okay. For me, is basically I personally regarding the reinforcement learning is strongly related to the causal inference, but that is not a traditional causal inference. I'm being honest with you. I don't think that's belong to traditional causal inference either under the Pearl's framework or like Robinson's framework for longitudinal type of this kind of the causal inference, or not even Don Rubin's the framework. But I think they're highly related because these are dynamic systems. And you want to basically change the policies so that you can see the effect from both the kinds of demands and supply side. And also this is part of the whole cities. Then this is the whole stuff is interact with each other and move forward. But I think when I working with multiple teams, Tony helped us to solve everything related to specific policy. And like when Shikai worked with me, he basically tried to evaluate all the systems, because I need to think about how to really evaluate every policy kind of Tony did, okay? But when they try to interact with each other, basically one on the optimization, another one evaluation. But when I talk with the people from the kinds of more senior administration perspective, they don't really care about too much about how do you using optimize it, how do you evaluate. They think from the more high levels, from the market perspective. Okay, that's more global the kinds of perspective. In that case, everything is under that umbrella. How much you can do it, because I think when I help manage, I always think about a causal, okay, in certain sense, because I want to really gain money for the company, and at the same time I satisfy our customers. But I think not yesterday when I attended this NSF review panels, well, one of my the officers asked me the questions regarding what's the future of the deep learning and the reinforcement learning. My comments in general, if deep learning does not pair with the applications, I don't think deep learning is, that's not too much can be done. And from that perspective, but I think the same thing happened to the reinforcement learnings. For reinforcement learnings, you really need to find the application domains. And then you combine with deep learning, with reinforcement learning, and with causal inference. And this is all these kinds of the tools we need if we're really working on these kinds of IoT-based markets. Okay, that's what we're talking about, the two-sided markets, all these kind of things. I think currently, if the people want to work at the IoT-based industry, I think that all the three knowledge set is important: deep learning, reinforcement learning, plus causal inference. And that's my personal opinion about the future, or like I think that's something is critical. That's my personal opinion. That's
Yeah, that's nicely put, I think. Yeah. So we mentioned about evaluation and also simulation issues. I actually want to touch more on that a bit. I'll just give you a motivating example that I have been thinking about after seeing some stories about pilots and their training program. In our civil aviation industry, right? Like pilots learn flying an aircraft. They first study the theoretical stuff, and then they train in the flight simulator, and then they go on to train with the certified instructor in the real aircraft. And then finally, once they have learned enough, then they pass the exam to fly alone. So that's so-called the solo flying. Right? And then after they have obtained their commercial license, they still come back to the simulator to regularly, polish and practice their skills. So these pilot training procedures seem to, produce all the reliable pilots that fly our flights, regular flights, right? And in reinforcement learning, so I'm just associate that with how we train reinforcement learning agents. And we train our agents often in simulation environment. And we also have methods like curricular learning, where you gradually increase the difficulty of your tasks, and knowledge distillation with teacher-student learning or imitation learning. But obviously, there seems to be still quite a distance from being able to train a purely RL trained pilot agent at the same level as a professional pilot. So this is what I have been wondering. So what are we missing here? We think that we are basically following a similar set of procedures in terms of training, and people, human beings, also train from novice to professional pilots. So there must be something missing here. So I would like to hear your perspectives about like this observation. So how about let's go round robin again, and Ling Long.
I think I don't know. I think from my perspective, I feel the simulator is very important. How you build a simulator, and in reality, it doesn't matter how well you build your simulator. It's always simulate the reality, and always a distance between the reality. And like Fan said, we need domain knowledge. Even we have very strong, very rich domain knowledge, but the simulator, like say, like 370, like this Boeing company, their simulator to train the pilot, it's you miss one point, one single thing, and it can cause a very big consequence. And also nowadays, I think for reinforced learning, the process to build a simulator, the experience or the to build a simulator is not that rich yet, and in order to have a very successful application, and we still have a long way to go, and maybe start by building different simulators in order to train better IR algorithm.
Yeah, I guess another a related question often from industry practitioner is that how much resource should we devote to building a simulation environment that's really high fidelity? Because you can always go to the extreme and put in more and more time and effort to close that fidelity gap. But is that really worth doing to push to the extreme, or should we devote the resource to something else? For example, maybe different kinds of environment, and try to improve the diversity or robustness. I guess that's a related question that I would like to ask the panel as well. How about we move on to Zhao Ren?
Yeah, I think at least one issue I have encountered about like training only in simulators, like if you want to achieve the level of driving, it's piloting some plane. I think the one possible issue, I think it's also a theoretical question, is that if we specify the reward, in a lot of cases, there's a phenomenon which I call like under specification, because given a particular reward, it can induce a lot of different behaviors, and a lot of those behaviors can be quite dangerous for practice. Like if you just if you're trying to train a robot in a simulator, and if you just set the reward to be reaching some goal point, right? And then the robot could walk in a very ugly way instead of working in the same way as a human. This is because like when we're doing the training, we didn't really specify like the energy efficiency, because I believe as human, we kind of evolved to be energy efficient. And that is why we walk in our way instead of like walking in a very ugly way. And also I think if you want to really achieve the level of a professional pilot, there are a lot of rules that we as human have already learned. Like we cannot fly too low, for example, in certain situations. And that kind of rules are not really built into the reward, because that's only the feedback for some robot, right? And we cannot really specify the kind of rules written in words into the reward very easily. And that gives rise to the problem of like, can we train a robot like just based on the preferences, like in a previous talk? I think that's another practical issue that kind of really make the training in a simulator really hard, because there could be a lot of possible bad behaviors which like maximizes the reward, but really does not make sense. I think that's the like two possible issues.
Let's see. So we'll probably need to spend more time understanding the dynamics in a more thorough manner, I guess.
And also put on constraints on more constraints to regularize the behavior, I think.
Let's see. Yeah. How about Fan?
Yeah, I think building a good simulator is kind of expensive in many cases. For example, I know Didi put a lot of efforts into building a very good simulator. And I think if you want to build a good simulator, you need to know everything about the whole process. You need to know how to model the transitions. You need to know what's the reward mechanism. So I think it's not easy for many, I mean, traditional industries. So I think that's a big problem. But so I think maybe offline learning is one of the promising approach for many real world problems. Because you only need to like collect enough data and you can do the offline learning, and you don't need to build a very realistic simulator. But there are still some problems about offline learning, right? So as I mentioned, you need to have very good sampling data. Otherwise, the improvement of the offline learning cannot be guaranteed. You don't know if the policy can improve a lot or not. And also, even though you have very good sample data, there's still some gap between the offline learning and the real world. So if you put the policy learning to the real world, I think there's still some gap. And for some companies, we need to confirm if they want to pay this cost or not. Maybe some of them don't want to pay that cost. So I think there are still a lot of challenges we need to face before RL can be applied to more industries.
Yeah, agree. Bing, do you want to share some thoughts?
I just want. I'm thinking. So, so how do us people to learn in a dynamic system? So, would you have some deep learning or reinforcement learning with brain science? So how to develop the next generation reinforcement learning that can mimic all humans' learning ability. Yeah, for myself, I think sometimes I will consider reward. Yeah, I will consider how to get my reward maximized to do learning. But sometimes I think I didn't consider reward. I just want to, for example, relax. Yeah, a good relaxation can lead to good profits in the long future, maybe. But this kind of things can model or algorithm to model that kind of different kinds of goals or reward in the learning agent. Maybe that's an interesting question to develop learning agents that can better mimic our humans learning. It's just an open imagination.
No,
Yeah.
I will talk about it. I think, Tony, I think in generally, because I think it's firstly it's impossible. There are several aspects. Because when you try to build a simulator, you need to think about the level of questions you can answer from that. Okay. And when you're looking at the problems at the individual levels, because you think about that's almost impossible to simulate that. And the current simulator at the most, you can simulate like more global levels things. And this is, you know, that the more you go to the low level or deep level, like personal level, and the cost is much higher. And because you need to connect more data, you need more computational power to simulate how does it feel regarding each individual as agent. Then you have to follow these people in a certain way, so that you can really model the dynamics associated with that level. But I think as a like senior manager in the department in the company, because they always count ROIs. You know, for doing research is okay if you have money from government. But in generally, that investment, I personally don't feel that is necessary. Okay. Because even you know that information, that doesn't really that means that they can bring in incomes to the companies. And that because the people are living a whole societies, the company is only part of that societies. And that's the reason I don't feel from the cost effective perspective, it's almost impossible to do that. And regarding to that's the I think even for our current simulators, okay. And as I said in the previously, you need a really because of when you're talking about simulators, that's the first thing you need to understand the level of questions, right? Each level of question have the cost and also the associated because the cost is related to the data and also related computational powers. Right? This is basically the question are related to each other. Okay. And therefore, then it's impossible for company to invest all the cost, a lot of money to do the very detailed levels because for company that's an investment. It's not very wise. I personally feel that. Good. And the next things because like all the simulation you did, and but that's only focus on one single policies. Okay. Or one aspect of policy. Okay. And that's okay. But if you like what I said in the previous comments, because because each of these kinds of policy, when you target it to like when you're talking about some stimulus, right? And then there's another level of questions that goes by is a lot of simulators, in particular, looking at the some specific policies. You're looking at only one aspect of the whole populations. Okay, even for your customers, you only simulate one aspect of that. Okay, but you know that in this when the market there are multiple policies that simultaneously exist. Okay, they operate on the customer. Okay, and also customer interact could react to all the policy you applied to them. Okay, and also interact with the environment. Okay. That things make the simulators almost impossible for you to generate it. You only can do it at a certain levels. Has to be to relative high level. That's the first comments. The second things, for all the simulators, in order to address certain level of question, particularly in the company, if you think about it from senior administrative perspective, what are the kinds of questions they care about it are not complete at a low level. Okay. They are thinking about, a lot of the more global economies problems. Okay. Who are our competitors and what are kinds of the other alternative like transportation policy tools are there that help the income of this of the cities and all these kinds of questions. You think about it, if you really have the simulators at that level questions you wanted to address, okay, and then that's the whole total different stories. But I think the simulator is important, okay, and but I don't in general agree with that aspect. We need to invest tons of too much money on that because this really sometimes it's not cost effective. That's my general comments.
So we basically should focus our investment on really on the aspects of the problem that we, or rather, you know, the top management is really concerned about, and that's probably
I think
bring more
regarding
cost.
to all your current simulator you have, I think that you need another level of the simulators to link the things to the more global levels. Because the thing about it, how could you using simulators to the help of the senior managers to make their decision? I think that's important. Okay, now you're still at the more at lower levels. Basically, I have the policies. I apply these policies. I generate a simulator. This is my reward. I do it. But you know that that's only influence a small amount of customers in certain case. Okay, but only one aspect of the whole operations in the company. But then you need to go to the whole high levels. That's the reason you think about it when we talking about the two-sided markets. Well, we also think about how to manage the customers, right, at more high levels. Okay. And think about how to really build kinds of the analysis plan or kinds of the strategies to operation that on that. But I think that the current simulators is not at a level yet. I think that's the confusion. But I think in generally, that's my second comment. You need to think about how to make your simulators to be useful for the senior managers to make the quick decisions on the kinds of the, you know, for the company. That's important.
Gotcha. Yeah. By the way, how are we doing in terms of time?
We can do the 2 until 12, 20, 25, something.
Okay.
Okay, ask another question.
Yeah. Yeah. Since you know, all of the panelists are from academia, professors from universities, so I have a question regarding education. I think that's probably the profession for all of you. So the first question regarding education is RL for education. We have RL for, you know, for ride sharing, for autonomous driving. I'm wondering what's the ultimate form of reinforcement learning for education if we are to apply reinforcement learning in this domain. And I think, in fact, nowadays, as we see a lot of digitization of education, it's probably natural to think that reinforcement learning would be applied to that domain. I think right now there's already some effort from the industry or academia to do that. But unlike, for example, reinforcement learning for autonomous driving, where we are pretty clear like how it's going to be appear actually, like it's going to replace a human driver. So reinforcement learning or the whatever autonomous driving decision module, decision engine should make all the decisions for driving, right? But for education, it doesn't seem quite clear to me like what is the ultimate form of reinforcement learning application in this domain. So I would also like to hear perspectives from the you know, professors here on the panel. So Linglong, do you want to go first?
Think for me, I don't think RL can, you know, one day reach the level to replace a teacher. And I'm the 76th generation of Confucius. I think Confucius once said one word, 因材施教. And I think our would have a very hard way to follow this rule. And there are a lot of reality things to overcome, like previous talk, how do we do this, simulators, and how do you define the reward? That's very, how do you identify, the students, emotion things? It's, even this online, nowadays because COVID-19, a lot of things are online, even these online things, well, you actually have a teacher, you cannot replace, face-to-face teaching. How, you have a machine to replace a teacher. And that's my opinion on this.
If we take a step back and let's say we focus on just maximizing the students' test scores, right? Is it more feasible to have some kind of a education?
No, this actually it's a lot of discussion even at university, like say for my university, and because it's online teaching, and we are human beings. The interaction is more important, and sometimes not only the knowledge and the emotion connection, the interaction can simulate more, rich result. And I think I don't know. It's really hard for me to imagine to do that.
Yeah, it's it's also not clear to me that, and therefore the questions. So Jordan,
yeah, I think one possible way of thinking about this is that perhaps we can actually model the students as a reinforcement learning agent. I think this is partly true because based on my observation, they are pretty greedy when they try to maximize their test score. And some of them are just, have limited rationality because they simply do not care. And we can probably use some kind of entropy regularization to model those students as well. But I think the major difference from the setting we're familiar with is that we do not have the direct control over a lot of things, right? We cannot force a student to learn. We cannot, ask them to do a lot of things and really, force them to do those. So mathematically, well, I have thought about this. Maybe a possible formulation is that we can treat this as the kind of a reward design problem, or some kind of model design problem where we can have an influence on the reward function or on the transition model, right? And then we can use some kind of we can treat this as a game, right? We're just a kind of a controller of the reward. We can encourage students, we can give them additional scores, bonuses, and so on to ask, to encourage them to do something. And then eventually we can model them as kind of different reinforcement learning agent, and they have their own context. For example, some are willing to learn, some are not, right? And then eventually we have a goal to optimize. Probably this is one approach to model this problem. But in general, I don't know. You never understand what the students are thinking about.
Yeah, that's actually a very interesting perspective, like modeling from the student's perspective rather the instructor's perspective.
Yeah.
How about Fan?
I think RL maybe can do some basic work, like for example in the elementary education. And I know there are a lot of Chinese companies, they do like this kind of things, but I think they only need to use like deep learning to do some supervised learning. And I don't think they need to use RL to do that, because I think for the elementary education, I think the questions or the problems, I mean, kind of simpler than like the university. But I think for some higher level education, like in the university, I think we still need a teacher. And I think IO cannot fully replace the responsibility of teacher. As Linglong said, we do online teaching for quite a long time, and we all find that the efficiency is pretty low because students don't pay any attention to what you are talking about because they cannot see you and you cannot see them, so you cannot guarantee the efficiency of the teaching. So if we suppose that we have an AI trained by RL, even though it knows everything, it can teach students, but we still don't know if the students they want to learn from the AI. So I think that kind of responsibility of teacher cannot be replaced by AI. And also I think we need some the students need some interactions with the teacher. I think that helps them to get more familiar with what they learn, and they can learn everything more faster. I mean, compared to just learning from a machine or learning from AI. So I think that's a key difference between a real human teacher and an AI teacher. So I think there's still a long way to go, but I think some basic works maybe can be replaced by AI in the future. But I think it cannot replace the everything of human teaching. That's my opinion.
Yeah, more of a system type of tool. Yeah. Hongtou, do you have anything to say?
No, I think in general, when you think about it from the education perspective, and it's very similar to for us like running business unit in a company. I think the most important things is not about equity itself. The first strategy is basically you really firstly you hire good people, right? And that means your education, you need to train teachers. They have to be good teachers so to satisfy some conditions, right? The second thing is you need to have some rules. That's important. Without these two, I think the education is a jerk. Right? And number three is when you're talking about how to improve it. Okay, that's related to simple causal inference. And you need to think about identify some key factors. And it's more like a supervised learning. And you want to improve the student scores. At least you want to, after you set up the baseline, basically the rules and plus the teachers, then that's actually the without these two, you can achieve like a 50%, the 50s. Then if you think of 100 is the best scores. And the next things you never think about is just supervised learning. I think if you're using the traditional supervised learning, you can push the 50 to like a 70s. Okay. And I think that's the reason you think about for all these kinds of business, like e-commerce, all kinds of like recommendation system, all different things. They don't really start with reinforcement learning at the first place. You think about it, for most of the things people are using nowadays, it's just the traditional statistical model, or just you think of machine learning model, right? You can push it about to another 70%. But when you're talking about using reinforcement learning, that's another level of questions you're thinking. You're dynamically looking at each subject, and you're looking at the students as a kind of as a whole or like a subgroup. But in that, because if you use the expectation, you're treated the subjects as a kind of average level, or if you work on the distribution, right, reinforcement learning. But in that levels, but you can use the reinforcement learnings to push that aspect. You need some policies or like tools basically to optimize it dynamically. In that case, the student score is getting high, but I still don't feel that you can like to the 70. You can choose 70s, maybe you add a reinforced learning, you can move to 85. But another 15%, 50 scores, I don't think the current reinforced learning can do it, because that's really goes back to either at the individual deep levels, okay, and or either at the very high levels, okay, and that is not that cannot be solved by reinforced learning. Okay, that's my personal perspective. Anything, I think that's the kind of logic I have when I try to do things.
I think that's fair enough. Yeah, and since there are a lot of graduate students in the audience of this conference and this panel, and also I think it will be a good question to close the panel. Could each of you give a little bit advice on what makes a good reinforcement learning researcher, or basically how does one prepare for a career in reinforcement learning research, whether it's in academia or in industry? How about we go from the Bing?
I don't have a question, but I think I just want to share my thoughts on education. I think it's very interesting. I just recalled Susimofe's talk on precision medicine. Maybe there is some analogy between precision medicine and precision education, because the objectives for both domains are human. Maybe the Susi's work can give us some inspiration to do precision education.
How about Linglong?
I'm a statistician, and my experience with reinforced learning is, I first found this area, distributional reinforced learning, is quite related to what I'm doing. One of my research area is quantile regression. So I start to be interested in this area. Then that's how I started. And also later on, I got an opportunity to do my sabbatical with Huawei Canada. And that's how I start my research in reinforced learning. I guess you first need to find a place where you are interested in, where you feel you can make some contribution. Then, yeah, you can start your career over there. But my story is quite different. Like I said, I'm a statistician. I came from statistics side, and that's why I need to find a sort of a sweet spot to get into it. Yeah.
Yeah, I guess that's also a perspective from doing the cross-domain research. Yeah. Zhao Ren, your turn.
Well, my personal experience was that I was trying to build a agent for playing the game of called King of Glory, 王者荣耀. And then I kind of encountered a lot of frustration because it's very hard to make things work, especially when you don't have a very fast simulator. And then I kind of look into the the theoretical properties to understand why that doesn't work. So actually, so from my personal experience, I think actually playing with those, you know, very practical settings would be very different. Would be very important for understanding the theoretic properties. And there would be a lot of you know, tricks that are typically ignored by theory, but turns out to be very useful in practice. And those tricks are basically the reason that it works. I think that actually motivates a lot of open theoretical questions.
So probably you should, like, students should not devote all of the times on the in the library, but you know, playing games does have some benefit.
Right,
in terms
right.
of, inspiring research.
Yeah.
All right. Fan.
I think I have some advices to the graduate students who are studying statistics. If you have interest in reinforcement learning, I think first of all, I think reinforcement learning is a very good topic for the students majored in statistics because it's basically an MDP problem, right? So MDP, I think all the statisticians are very familiar with this topic. So I think reinforcement learning is not far away from statisticians. And also, as Linhong mentioned, distributional reinforcement learning, what we are working on, is very good topic because it borrows idea from quantile regression. And I know a lot of researchers and students in China are working on this topic, quantile regression. So I think maybe distributional reinforcement learning is a starting point for many people if they want to do some research in reinforcement learning. And also, I think for a lot of statistical students, I think the coding skills is very important because we are faced with a lot of complex environments. So if you want to test your method in, like, for example, the array environment, so you need to have a very solid programming skill. So I think that's maybe we need to, the students need a lot of practice to improve their coding skill. That's my opinion.
I would think MVP is a operation research topic.
No, I just want to add, there's really no boundary on data science. I don't know where it is, but anyway, yeah.
Yeah.
No, I just happen to catching that. Yeah, I don't know. How do we quantify nowadays who belong to which, right? Zhaoran, are you belong to optimization or statistics? I don't know who you are. Right?
Yeah, really, I don't know either.
And I do not know because I was growing from statistics, right? So people think I'm a statistician, and I like to be a statistician. But do I do any less finance, quantitative finance than anybody doing financial econometrics? I do not know that, right? Nowadays, I think we help my student at operation research and financial engineering. I think I'm just as operation research as anybody else in operation research. So therefore, there's no boundary in data science. I think setting a boundary is dangerous for anybody. Anyway.
Yeah.
Yeah. So yeah, Hongdu. So as a matter of fact, right, I think I belong to 10 departments, right? At Princeton. So,
That's a good point.
so there's no boundary. Just to prove one more. Sorry, Hongdu, go ahead.
No, I think Professor Fan comes in completely correct. I think my personal feel that I think the traditional statistics methods are still important, but I think because the one thing is I'm always thinking about application itself, and given the fact that last 5 years or 10 years, I think because of the development of Internet of Things, I think the one things people always think about, why is AI is so important because you can using IoT and this kind of things to digitize all these older markets. Okay. And there will basically, there's a lot of opportunities for doing that. Because when we have a superpower, a lot of abilities to connect more informations, And also we tried to digitize the whole kinds of markets. And then in that sense, we have a lot of data. The more data you have, you get a lot of model informations. And the one thing is basically for all the markets, there's a different level of questions you need to solve, given the data you have, okay? And therefore, there's a lot of opportunities over there. But when you collect the data dynamically, the reinforcement learning becomes super important. And but my personal feel that the traditional machine learning or statistics are important, but these days it's not enough. But given the scale of the data, amount of data you have, I think the reinforcement learning definitely is a very great tools you needed to know. And also deep learning is also important. I think deep learning has this kind of spatial kinds of representation and also a lot of kinds of powers for different questions, different problems. I think that's also important. But I think at the high levels, I think causal inference is also important. But I'm not talking about the traditional causal inference. But and under this kinds of new, more complex environment, what is the right causal inference framework by combining all these kind of existing tools, in particular reinforcement learning? I think this is the future. But that's the reason why I spend a lot of time to sell this concept and also ask the people to go into the specific areas and develop all those skills, a set of the knowledges. And then I don't think there's the kinds of very mature theory behind it yet. But I think 2 years ago, Michael Jordan talking about two-side markets. But I don't think at this moment it has a very complete pictures about what is should be two-side market. We try to build the same thing, but we still have, I think, understand one aspect or one proportion of that two-side markets. But in generally, I think this area is still open. Okay, but that's my key point. But I also mentioned that like Michael, these people are working on the health. The main difficulty with health is the way you collect the data, what kind of information you can use it. And there's a lot of regulation and all the barriers for you to get to the data to make inference about certain level of questions. But if you're working on in the other markets, it may be much easier to get all kinds of data you need to push these areas much faster compared with the health. I think that's basically, I think that's my personal opinion. That's the reason I think the reinforcement learning and causal inference and all other traditional stuff are all important. Okay, there's no boundaries behind it because this is a whole open areas. You may can define as a kind of, I think for all the students, you may working in the specific areas and try to develop the whole method behind it. Okay, that's the future. That's my personal opinion.
Well, so since you guys are advising to students, so let me say a few more, to what really said. But there's always have short-term future for students which want to find a job and which want to, establish a career. So I think then you have a short-term goal, right? There's also a long-term goal, right? So in other words, how the world will be always changing, will never be the same. What is hot today will not be hot tomorrow. Anyway, not literally tomorrow, but will be one day. So, however, the fundamental principle, the principle behind mathematical sciences, behind statistical thinking, behind computational algorithms, always remain the same. So, in order to capture the opportunity, right? So you also had to do something like in short term, you were able to at least reasonable success in one case studies. So if you never have any case study successful, you'll be like some pure mathematician. So we've never been able to understand fully what is the problem going on. So I thought it's very important for students at this moment to understand what is the current I mean, what is the intermediate goal, and then the long goal. Don't forget the long-term goal. Your long-term goal is not really to cruise with the future, because you cannot predict the future. However, you can always manage in the future direction, and in this case is the foundation, the understanding that you get from your classes. I think that's very important. I don't believe anybody or us who are standing here today talking to you actually learn anything when we were in the graduate school. So it's very different. The world always changing. However, the principle will guide you, will lead you to the future.
I think we have learned a lot from this panel. Let's thank all the panelists today. And so I'll close the panel here, I guess. Thank you.
Thank you. Good night.
Thank you all.
Thank
Good
you.
night. Good day or good lunch.
Good night. Good day.
Good night.